Okay, good morning, everyone. So thank you for coming. So welcome. I hope you had a good trip here to Athens if you came from abroad or from another place. So as you, like many of you know, this is an annual event. It has been established now for some time. So this is the 9th installment of the annual theoretical physics meeting here in Athens. So this year we made some additional some modifications. So it's the first time that we have this third day, so which is now first like in this year's program. So we introduced like specifically like a young researchers like session. So the idea is that like there are several like of you younger researchers like in theoretical physics that we would like to give like the opportunity to present your work, so to get to know the broader community and for the rest of the community to get to know you. So we hope that we'll be able to continue this, like in the subsequent years. So this depends, of course, like on available funding. So the funding for this event has been traditionally provided by the University of Athens. So this year and also the previous years. So we are very grateful to the University of Athens for this contribution. And so this is like an event that we hope that can help to kind of consolidate the theoretical physics community, especially the Greek community and like dear friends. And we hope to be able to continue this in the future. So now I would just like to mention like a few practical things. So there's no lunch provided. So there's a lunch break later today. So for lunch, like usually we just go around, in the local stores. So if you want, you can follow a local, to guide you, to the places that are available. So also, please, in general, keep your belongings with you, especially during the lunch break. So it's not a good idea to leave them in the room. So the room is probably locked during the lunch break, but it's a good idea to keep it with you. Also, there is Wi-Fi in the room, so the only Wi-Fi available, unfortunately, is EduRoam. So if you have EduRoam from your institution, then it should work here. And the other thing I should mention is that we should all try to be punctual, with all the talks, so that we get out, by the end of the sessions, because they are very strict about this. So we have the room until some particular time, and we should be able to evacuate the room by that time. So I think that's all for now. So without further ado, I think we can start with the first talk. So the first speaker is Marios Galanis. So we can have this.
Okay, I'm using this.
Okay, so we're ready to start. So as I said, the first speaker is Marios Galanis from Perimeter Institute, and he's going to tell us about probing H0 and resolving the AGN disk in ultra fast photon contest.
All right, thank you. Thanks to the organizers for the opportunity to present my work. So today I'm going to tell you about astronomy and astrophysics and about a new way that we found of utilizing an old technique to do exciting new things that no other technique can do. I also work on particle phenomenology, so Mina will talk about some other thing involving neutrinos tomorrow morning at 10 a.m. So tune in for that. Okay, so this work we did with Neil Dalal, Charles Gamy, Sam Gralla, and Norm Murray, and involves interferometry. So to begin with, let me remind you what interferometry looks like. So imagine you have, interferometry is a very simple thing. You have two telescopes, telescope A, telescope here, and the distance between the two telescopes is called the baseline, and I'm denoting this with B. The resolution of such an instrument is given by what you know. from your undergraduate optics. It's the wavelength that you're observing at, whatever this wavelength is, over this baseline. And if you plug in numbers in this, and you plug in numbers for radio telescopes, for example, what the Event Horizon Telescope does, the wavelength is about 3 millimeters, the wavelength they're observing at. The baseline is about 25,000 kilometers. It's the radius of the Earth, essentially. So you have baselines that are basically north-south pole. Now, the resolution of this instrument, so this ratio, if you plug in the numbers, is about 30 microarc seconds. If this unit doesn't tell you much, just remember the 30 microarc seconds, and then we'll contrast this with AGN angular sizes that are what I want to look at. So by doing this, microphone is off. Ένα, δύο. Έχει μόνο ένα μικρόφωνο. Δεν νομίζω ότι παίρνει δύο. Ναι, όχι, αυτό πρέπει να δουλεύει. Ναι. Ναι, αυτό πρέπει να είναι, okay. Αυτό, ναι. Εκτός αν είμαι muted. Είμαι muted. Είμαι muted. Sorry. Okay, τώρα πρέπει να είναι okay. Ναι. Okay. Okay, good. Oh. Okay. Right. So if you do this in radio, what people did, in 2017 and later, is take an image of a black hole. So the resolution in this image is about 30 microarc seconds. You see here the scale, and the fuzziness is exactly because of this fact. The radius of this black hole is almost on the order of the resolution of this instrument. Okay. This is the smallest thing we've been able to resolve on the sky by using these extremely long baselines in radio wavelengths. The observable of intensity interferometry, of Michelson interferometry, is called the visibility function, or the two-point correlation function of electric fields. And if this doesn't tell you much, essentially it's the 2D Fourier transform of whatever you're observing on the sky. So take the sky image, Fourier transform it, you get the observable. The converse thing is how you measure it. So you measure this visibility from the telescope, you invert the Fourier transform, and you see the image on the sky. So this is in radio. And this theorem is very well known. It's the van Sittert-Zernike theorem. Very good. So I told you people did this in radio, but you can also ask, can I do this in optical wavelengths? Because lambda now is much smaller. It's a micron, half a micron. Optical wavelengths. The problem with optical wavelengths is that the baseline is restricted to be something small. So instead of 25,000 kilometers, about 300 meters. There are arrays that do this. For example, the CHAR array or the gravity of the European Space Agency. And the resolution of this instrument is about 200 microarc seconds. The reason why the baseline is restricted is because when you're trying to measure an electric field, you can do two things. One thing you can do is record the electric field locally as a function of time. So record every oscillation. And this is what the Event Horizon Telescope does. So you basically record the electric field as a function of time, and then you do your correlation offline without ever bringing the real light to interfere, the two light beams to interfere with each other. In optical wavelengths, you cannot do this. If you convert this to a period, this is about a femtosecond. There is no technology that can record the oscillation of light to within a femtosecond. So what you have to do is bring light physically together and then see the interference fringes happening in real time. And this is what they do. So you record light, you gather light with telescopes here, and there, somewhere up there, and then you bring in some central facility to do the real-time correlation. And then you measure out the fringes. The other thing that is very hard, it's not only that you cannot record the electric field as a function of time. The other problem is that you need to know your baseline. You need to know this distance to within a wavelength. So you need to know your 300 meters to within half a micron if you want to do this, because you need to know the phase of the electric field, and the phase changes every femtosecond. So it's very hard to do Michelson interferometry over longer baselines. But of course, the question, right, and this has been used to measure basically big things on the sky. For example, sorry about that. For example, Betelgeuse is the first thing that Michelson himself in the 1920s observed with his 6-meter Michelson interferometer. So there is a question, what could we gain if we could keep lambda small, the wavelength small, but also the baseline as long as we can? Is there any technique that can do this? And the answer is yes. So this effect, it's called the Hanbury-Brown and Twiss effect. It was proposed in 1956 by Hanbury-Brown and Twiss. Its first application was in astronomy, but it's this effect that basically kickstarted the entire field of quantum optics and photon correlation functions. So I will explain to you this effect in the next few slides, and I hope that if you take at least something out of this talk is this new fun physics fact that we don't necessarily learn in our studies. So imagine that you have a tuning fork, like a perfect monochromatic wave. This looks like this. This is the electric field in arbitrary units as a function of time. It's just oscillating. Okay, let's make this a bit more interesting. Let's add 2 sine waves, slightly detuned, so A and A sharp. Now you get these beating modes. So you get a fast oscillation that happens on the central frequency of basically A, the central frequency, but you get this envelope that is parametrically larger. The reason being these 2 frequencies are very close together, and the envelope happens at the difference of the 2 frequencies. Okay, so it's the usual beating modes that you get from slightly detuned tuning forks. So now let's do the other thing. Let's add all the frequencies in between as well. And now you have many sine waves, and it looks like this messy thing. Again, it's just adding many frequencies, basically a spectrum that has a finite width from A to A sharp, and adding all these sine waves with random phases. Mathematically, this is what it looks like. I'm just adding sine waves with central frequency omega, some spread that is less than the central frequency, and then each one has its own random phase. So I'm summing all the sine waves, and phi i's are just random. So this is just a random stochastic field. Okay, so we have this electric field. Let's look at the intensity, which is basically the square of this thing. And let's zoom in. So zooming in, you see the intensity with the black line, and then you see the fast oscillations of the electric field with the blue line. Now here I'm assuming optical wavelengths, so the time scale is a femtosecond. Okay, so the time scale for these oscillations here is femtosecond. Though this time scale, this large envelope has a longer time scale. And again, this longer time scale is given by the spread in frequencies. It's not given by the central frequency. So this is given by delta omega instead of omega. Okay, good. And now I don't care about the fast oscillations. As I told you, there's no technology that can tell us anything about these things. We cannot record it, so I'll integrate them out and then keep only the envelope. So if you have a telescope that is perfect, it has a perfect photodetector and measures photons as a function of time, you can ask the question, what is the spread in the number of photons that I'm measuring? What is the variance? So this is number of photons I'm measuring minus the mean number squared, average value. And whenever you measure photons from any source, you get shot noise, right? It's if you have a laser, the uncertainty of the amplitude is square root of n. The amplitude is square root of n, for example. The intensity is square root of n. So you get this n. And this is what you would get. So a laser would have a perfect laser would have constant intensity as a function of time, also in the number in the limit of infinite photon numbers. So the intensity as a function of time for a laser would be this dashed line here, which just, you take the modulus of sine, it's basically 1. However, with this many sum of sine waves, this stochastic field gives you extra fluctuations that go like n squared. And I will call these macroscopic fluctuations of intensity because this is order 1. This can be, 1, this can be 3, this can be 0.5, right? So this is not just shot noise. It's not just the fact that, the number of photons is finite in whatever you're looking at. It's the fact that you get these random fluctuations in the intensity that are order 1. Now, the only way to see these things if you have a photodetector that is precise enough that can resolve time scales that are of the inverse frequency. They may not be a femtosecond, but they may be a picosecond, right? So any telescope that you use that has CCD cameras, for example, these are milliseconds. There's no way you can see these oscillations or these fluctuations with something like that. So we need other photodetectors to see these effects. And I want to stress that this is something that is fundamental in light, in any source of chaotic source of light, whether this is a star or if it's the light bulb in your office. You always get these macroscopic fluctuations. And again, the reason why people don't really talk about this is because when you ask someone, what is the flux that I get from some star? What is the flux from Sirius? They give you a number. They never tell you this number is uncertain to order 1, right? The reason being that when you observe a star, you observe over long times. So you never see these very short time fluctuations. You just see the mean, which is the dust line here. Okay, so we want to take advantage of these macroscopic fluctuations and do interferometry with them. So you have 2 telescopes now. You're staring at a star. Here I'm having Sirius, and both stars see the exact same electric field goes into both telescopes. There is a time delay because one telescope will be geometrically closer to the star than the other telescope. So if you tune the time delay correctly so that both telescopes see the exact same peak as a function of time, then you can ask the same question: what is the correlation now of the photon counts in telescope 1 times the photon counts in telescope 2? And again, you see that if you put these telescopes together, you get this n² effect, the number of photons squared, these macroscopic fluctuations. And by the time delay, I'm saying that this correlation function, this Fourier transform, if you want, normalized to 1, has a peak at some non-zero time, which is exactly the time to cross, the time the wave needs to go from telescope 1 to telescope 2. Very good. Now let's say that I detune my time delay, or I don't tune my time delay correctly. Then the other telescope sees just some other random fluctuation in this field. So there's no correlation. There's no correlation between when this peak is happening and when this dip is happening. So I lose the effect. And by seeing this loss of the n² extra correlations, you can do interferometry, because losing the effect means that you get some information about spatial scales. Right. However, I told you that no photodetector is basically good enough to femtosecond, so I cannot really put my telescope perfectly in this time axis. So in fact, my telescope is a bit fuzzy, which is the statement that intensity interferometry suffers a suppression in these extra correlations. They are a little bit washed out. And they're washed out by the coherence time of light. Basically, the inverse of this width here is this coherence time over the resolution of your photodetector, sigma t. So Tc is coherence time of light, sigma t is whatever your photodetector has. If it's a CCD camera, it's more than a millisecond. If it's detectors that I'll show you in a bit, it's more like picosecond. So the observable, again, is a 2-point correlation function of intensities now. So it's 4 electric fields, not 2, as Michelson interferometry. And you can compute this, and you find that instead of the Fourier transform, you get the modulus of the Fourier transform squared, which is to say that this technique loses some information. The Michelson interferometry measures a complex number, amplitude and phase. This technique measures just the norm, the sum of the real and imaginary part. So you do lose some information. Also, the signal now scales like the number of photons squared, because you have 2 intensities. You have this visibility function, whatever this number is, normalized to 1. So think of this as just 1. And then you suffer this suppression that I told you before, the fact that your photodetector is not perfect, and you are suppressed by the coherence time of light over the photodetector resolution. So this is something like a picosecond. Back in the 1950s, this was 10 nanoseconds. So this could be a 10 to the 3, 10 to the 4 suppression of the effect that I'm trying to look at. And the noise goes like n photon, because it's a higher point correlation function. From this, you can see that the signal to noise ratio for usual interferometry is just square root of n, because it's a lower point statistic. This is n. So I also need very bright sources to be able to see this effect, because n, number of photons per time, is a small number. So I need stars that are bright. And then the question is, what can I learn from these stars? So I need some real number to measure, because I measure a modulus here. And in fact, if you take a uniform illuminated disk, so some uniform intensity and just some disk of some radius theta s, you can compute the Fourier transform. You find that it is exactly real. It has no imaginary part. And this is what I'm plotting here. So as a function of baseline for Betelgeuse, which was the first star that we resolved with Michelson interferometry in 1920s by Michelson and Pease. And you can see that basically this visibility, what this function does is, if it's 1, then you haven't resolved your source. For you, it's like a point source. Once this visibility falls below 1, it's when you start resolving the source. And whatever sets the baseline in which you fall down from 1 is what sets the spatial scales on the star. So here the only scale is the size of the star. So this is what I'm resolving here. I start resolving that 1 over k theta. I have completely resolved the star at wavelength over theta, which is the usual diffraction limit. Okay, so the traditional approach suffers many limitations. One is the coherence time, and the other, because it's a femtosecond. If you have just a broadband thermal light, the spread is on the order of the frequency, so it's femtosecond. So the traditional approach is to use a filter. A filter makes the bandwidth smaller in the lab, so you can choose your bandwidth to be much smaller than the central frequency. So now you can make this a picosecond if you have a very good filter. And the other thing is you try to make TC larger and sigma t smaller. So you use PMTs, which are fast photodetectors, to make sigma t larger. Smaller, better resolution, time resolution. And in the 1970s, they measured about 30 stars in the Narabri Observatory. They used PMTs. We still use PMTs today. Their time resolution is 10 nanoseconds. So you still see that this separation is quite large. It's about 3/4 orders of magnitude. And we still use PMTs today with these Cherenkov telescope arrays to do intensity interferometry. Nowadays with very big detectors. Now, as I told you, it's also a shot noise limited measurement because the ratio goes like the number of photons. It's a steep function of the number of photons, so we also need large mirrors. And finally, nearby sources so that the flux is large enough. Okay. Now, if you put everything in and you compute your signal to noise ratio, you'll find that the stars you can observe with this technique, the traditional approach, is about 2. So these are stars that you can see with your naked eye. These are extremely bright objects on the night sky. Very good, but I'm telling you that I want to look at AGNs. So how do I do that? There are basically 3 ways that all add up to give you a large enough signal to noise ratio. First one is we use new technologies that do very fast photo detection. These are called SNSPDs. They stand for nanowire superconducting photodetectors, or avalanche diodes that have a reverse bias current that can give you single photon counts. All these detectors basically measure every single photon that you throw at them with some very good efficiency. Their time resolution can be 10 picoseconds. Okay, way better, 3 orders of magnitude better than what they used in 1970s. And I want to stress that these are commercial devices. You can go and buy them off of eBay, Amazon. Well, not Amazon, eBay. And the other thing is today, compared to the 1970s, we can use spectroscopy. So instead of just using a filter and throwing away all the photons that I get from my broadband source, I can instead disperse the light with a grating and then measure each channel individually. And today you can go and buy an off-the-shelf grating, for a couple $1,000, and the resolution can be on the order of thousands, so 5,000, for example. And then you gain in your signal to noise ratio very schematically by the square root of this number. So I'm making this ratio much larger. I also gain by a factor of 30 by the square root of 5,000. And by doing this and having a very large collecting area that we know how to build today, so today we can just build huge telescope arrays that are sort of crappy mirrors. But if we don't put many restrictions, many tolerances on the mirrors, such as diffraction limited mirrors that the best telescopes in the world have, but we just want a big photon bucket, just collect all the photons. We know how to do that very cheaply. So we have arrays like the Cherenkov telescope array. The total collecting area is something like 5,000 square meters. No, that's wrong. Sorry, 2,000 square meters. It's enormous. These are 23 in diameter, these telescopes here, these 4 large ones. So by adding all this together, we can go and look at AGNs and open a new window for astrophysics. So what are AGNs? Your 1-minute introduction is they're supermassive black holes accreting gas. Most of the emission in these galaxies comes from the accretion disk. It doesn't come from the stars. That's the definition of an AGN. The ISCO, the closest orbit closest to the black hole, you can think of this as maybe technically it's the innermost stable circular orbit, but it's close to the horizon. It's order 1, similar to the horizon. It's about 0.2 to 0.2 to 0.02 microarc seconds, depending on the distance and the spin. And this is extremely small. This is 2 to 3 orders of magnitude smaller than what I told you the resolution of the Event Horizon Telescope is. So you would need a baseline Earth-Moon basically to do that. Even the mean radius of emission, where most of the emission comes from, is about 5 microarcseconds, so still an order of magnitude smaller than what the Event Horizon Telescope can do. And the baselines that you need to resolve these things in optical, not even radio, optical wavelengths, are about 400, hundreds to thousands of kilometers, or tens of kilometers for the mean radius. So you can do this from the ground by using this intensity interferometry technique. You don't need to go to space, that Event Horizon Telescope wants to do, and spend billions of dollars to do that. So we found two applications in our paper. The first application is by adding all these technologies that I told you before. The first application is you resolve nearby AGNs and study their physics in great detail. The second application is you can resolve the broadline region, which I'll tell you what it is in a second, and measure Hubble in the late universe, the Hubble constant, the expansion rate of the universe, and chime in into the tension, the Hubble tension. Okay, so AGN disks, again, I'm showing you here some visibility as a function of the baseline. Now, it's not just the star. This is sort of a busy plot, but I'll tell you what to look at in this plot. Now, this is not a star. It's not just a uniform illuminated disk. I'm taking a very naive profile, let's say a Shakura-Tsunaev profile, and I also vary the index of the Shakura-Tsunaev profile. Okay, so this is just a toy model, just to show you what is happening. So you see this visibility function, and the key point is once this visibility drops from 1 is when I start resolving the first scale in whatever I have. So at small baselines, I can resolve, let's say, the mean radius of emission of my AGN. These are not, let's say, here. And at longer baselines, I can see finer and finer spatial scales. So for example, the smallest scale, which is the ISCO, for example, appears here. And this is just for different, mean radii of emission and different inner radii, you get different curves, but basically that's the point. When you want to make this smaller than 1, and the point is that this thing fits in the Earth, on the surface. So you can do, again, a very simple, very naive Fisher estimate. And what this is showing you that if you put these numbers in with the SNR that I told you that you can achieve with reasonable arrays, commercial devices, and 24 hours of observation, the SNR, signal to noise ratio, is about 3,000. So you can measure a lot of parameters, is the point, in this very simple toy model. And I just want to tell you that, for example, the innermost radius you can measure to 13 sigma, and the slope or the inclination you can measure to many, many sigma. Now, this is, of course, a very simple, naive profile. I'm not claiming that you can measure, let's say, the spin to which this number depends on, to 13 sigma. But I'm telling you that you have enough SNR to see the finest scales, the smaller scales on this AGN object. So you can learn a lot of physics by doing this. In principle, you would do a GR-MHD simulation and then fit your data to that. But this is telling you that you have enough power to look to see fine details and study physics in great detail. So why this is useful, I'll just flash a couple of examples. I won't go into details for the interest of time, but you can probe the unification model of AGNs, for example, correlate the inclination with the AGN type that people believe can explain the different models of AGNs that we see. This would be a huge success for AGN theory, for example. And there's no other way to probe this unification model. You need to resolve the AGNs or measure the inclination. Whatever, if what you have is not a thin disk, which is the simple example I showed you, you'll have different structure of the disk, you'll have different slopes, different intensity profile. You can measure this very, very well. So departure from classical disk theory, warp disks, magnetic fields maybe change these effects. And at the very end, maybe, I'm speculating, you could measure the innermost environment of the black hole. Maybe you could measure the spin. If you're interested in beyond the standard model physics, maybe this is where you might go and look at, for example, black hole superradiance. If you know what this is, cares about the spins. So maybe you can measure a spin and look for ultralight beyond the standard model particles. Again, I'm not going to go into details. But I want to stress out there's no other way to do this. You need to resolve AGNs to do this physics. So the second application is measuring Hubble. So to measure Hubble, you need the following. You need an angular size that is some real size over some distance, okay, to some cosmological object. This you'll get by intensity interferometry. As I told you until now, intensity interferometry measures angular scales on the sky. You need the dimensionful scale L in seconds or in centimeters. This we get from reverberation mapping that I'll explain in the next slide. And finally, to measure Hubble, you need the redshift. Now, the redshift we have because the objects that I'm going to look at are line emitters, so you can measure radial velocities and find the redshift. So basically, you measure theta, you measure L, you solve for D, and D gives you Hubble. It's very simple. So reverberation mapping is the following. Imagine you're an observer, this black telescope here. It's an effect proposed in the 80s by Blandford and McKee. It has been used since then to measure sizes, basically real sizes of AGNs. So imagine you have a telescope, you're staring at an object, and this object does all sorts of crazy things. The accretion disk fluctuates, it has very, very complicated physics that we don't really care about. Here, what we care about is the fact that there is light coming directly to you, the observer, and there is light that heats up the outskirts of the AGN. So accretion disk is about GM away, a few GM away from the black hole. This out here is light weeks, light years, light months, more like light weeks, light months away from the black hole. So it's very far. And the light emitted from the black hole heats up the gas here, and this gas cools down by emitting a line. So the accretion disk gives you all wavelengths, X-rays, optical wavelengths, infrared emission. But the gas at the outskirts, which is called the broadline region, gives you just line emission. So you can look at the, let's say, H alpha line or H beta line of this line emitter out here. Okay, and this is why it has a different. It's red. If you look at H beta, it's 650 nanometers. It's red light. So this time delay, you can measure this time delay as an observer on Earth, and this gives you an estimate for the physical size of the AGN. It's the time for the light to travel from here to there. Very good. So just to guide your eye, this is sort of what data look like for reverberation mapping. On broadline regions, they're called broadline regions because they're basically rotating and they have a large velocity spread. Yeah. Oh, the SNR scales linearly with that. Yeah. So you suffer a suppression, but this is all integrated. This is all taken into account in the estimate I showed you. Yeah. Very good. So you see the normalized continuous flux here at all wavelengths. This is just arbitrary units. We don't care about the units. The point is that this you see in all wavelengths, and this you see at the single line. Okay. At some time later, right? So you measure the entire flux, and let me guide your eye. You see that this dip in the total flux that you see from the black hole happens here. It happens a little bit later in the line. This peak happens a little bit later in the line, and this other dip happens a little bit later in the line. This is days here, right? So this is a few days later. And this gives you an estimate. This time delay here gives you an estimate for the physical size of the AGN. Of course, the actual thing you do is you measure the full transfer function of light starting from the central black hole and going out to the outskirts of the AGN. But the toy explanation is this one. So we have the real size, and the angular size then is very simple. You just do your intensity difframetry, and you measure that. So that's it. So then you can put in your SNR for reasonable parameters and for different AGNs, and you can marginalize over all the parameters that you put in your broadline region model, sizes, slopes, inclinations, all these things, and then measure just the distance. Ask what is the error I get to measure the distance. By the way, all the other parameters are interesting for astrophysicists. They tell you things about these broadline regions that no other technique can tell you. But let me just ask about Hubble and how well I can measure the distance to the AGN. So here, this contour plot is the SNR, the signal-to-noise ratio in this Hanbury-Brown and Twist measurement. For the parameters I showed you earlier, for the AGNs, this is about, it gives you an SNR of about 73. So reasonable parameters basically live up here for bright objects. And then this is the SNR in reverberation mapping. So the red line basically here tells you how well you can do today. We just took the numbers, the errors from actual measurements. In fact, we were a bit pessimistic. We chose 30% error. We actually think that it's more like 10% error. And in fact, this is a shot noise limited measurement by talking to people that do these reverberation mapping observations, which is to say that what they've told us is they don't have a real reason to just stare at AGNs longer and do these measurements. So if you give them a good enough science case, they can just improve this SNR by a bit. And you can see that these contours, which give you the error in how well you can measure the distance or Hubble per AGN, so this is for one object, can be down to 3%. And it's even limited by reverberation mapping. It's not even limited by my intensity interferometry. So I can go down to 1%. Roughly 3% is so the tension is a 5 sigma tension. If you can measure this to about 3%, or better than 3%, maybe 1%, you can start chiming the tension to better than 3 or 4 sigma. So this can give you a real, completely independent measurement of Hubble in the late universe, independent of any supernovae or assumptions about stellar structure. Very good. That's all I want to say. So my conclusions. I introduced to you the new idea of long baseline intense interferometry that is only achievable because of these new technologies. And you can think of it, the takeaways, you can think of it as doing interferometry in optical wavelengths over as long a baseline as you want. The way we can do this is because we have new technologies and we know how to build large and cheap photon buckets. And the applications I told you about are geometric measurement of the Hubble constant, enough to resolve the tension, pun intended, detailed properties of AGN disks, and you may even have sensitivity to the innermost part of the disk and even measure things about strong gravity near the horizon. So thank you.
Thanks, Mario, for the nice talk. So are there any questions?
Do you have any preliminary results about H0, or when do you expect?
Right, so the problem with this is that nobody has thought of doing this long baseline intense interferometry, so we don't have the telescopes. We do know how to build these telescopes, and we do have arrays that are going online that have these big collecting areas. The problem is they don't have the baseline that is needed. So what one wants to do is build a dedicated array to do these things. And we've been talking to people in Arizona who want to build about a 5,000 square meter telescope to measure basically spectra of exoplanets. And they plan to use large baselines if needed. So we think that in the next 5 to 10 years, there will be an instrument that can give you some things about it. So the other thing, so Hubble, in fact, I think that in principle you can do it with instruments that exist. You just need to take time in some of the large telescopes, let's say Keck and something else that is far enough that you can resolve the line. And I think it's the first thing that you will measure, because actually, maybe to not 3%, but 10%, because actually you can do this with only 1 pixel. So you can just put one single diode, stare at the sky, and get a 10% error for nothing, basically. Just a huge collecting area and a good photodetector.
Any other question?
Another one. Now it's about the last application.
Yeah.
How sensitive is the sensitivity of the underlying mathematical model about the
Right. So in principle, you'll do some, you'll do the same thing if the Event Horizon Telescope does. So do simulations of GRMHD probably, and then feed your data to that. Especially for the innermost parts of the accretion disk, which is very complicated. For the broadline region, there may be ways to use analytical models, but sensitivity to the model. Okay, so this is sort of an open question. Okay, so you're measuring Fourier modes, right? And you want to reconstruct a real image from Fourier modes. So this is sparse in general if you're doing long baseline interferometry. It is sort of an open question how dense your array needs to be so that you're completely model independent and you just take an image exactly like you do with an actual telescope. But if I assume that this is sparse, then it is model dependent in the sense that you need to give it a model so that it can give you out the parameters of the model. And then you can do statistical analysis exactly like people do in actual interferometry as well. Yeah. The toy example I provide is just so that you can do computations analytically for this paper, but the follow-up should be actual simulations from simulation people.
You also mentioned rotation like a couple of times. So can you actually measure the rotation? Like in particular, can you tell if an object is extremal or near extremal?
Oh, the black hole.
Yes.
Right. So this is also sort of an open question. We looked at it a little bit. You do have some sensitivity to the spin of the black hole. the problem is you're measuring modulus squared. So the spin is sort of, you can think of it as a, let's say, quadrupole, and then a dipole, and then this gives you some degeneracy with monopole times quadrupole if you expand in multiples. So one needs to look at it more carefully. And the other problem is it's not simple, because it's such a small scale and the SNR is not a million, it's about thousands. It's not like you can pinpoint exactly. You see some of its features in the fold down of this curve. So for example, here, you can see that you get this dip from the hole itself, if the hole is sharp, which is not necessarily the case. So one needs to basically have models, do simulations to see how the gas falls back in the hole. But because the SNR is about 1,000, you can draw a line here, and you see that you don't really resolve the fold down of the sharp hole. You measure only the fold down here, the slope here. So it is a little bit sensitive. It's unclear whether you can measure it to very good precision, or you can just say that the black hole is rotating. If it's extremal, if it's 0.99, for example, spin, you may be able, because the ISCO is very different, right? So you would expect an ISCO here. You can have an estimate for the mass of the black hole and then see where the fall off is happening and things like that.
Okay. One more question, yes.
Also in the first application. So you assume that the temperature drops with the distance as a parallel.
Yeah.
What are the values of n that you choose? Is it critical for your design?
So it is not really critical. Yeah, I'll tell you how it depends. Yeah, thanks for the question. So I chose the Sakura Sunaev n. I think maybe I should have put n over 2 there. Sorry. So when I ran the model, I chose the Sakura Sunaev one. It is sensitive in the following sense. If the slope is very steep, then the mean emission peaks closer to the black hole, which means that most of the emission is coming from the centermost regions, which means that the entire curve is shifted. All the things are shifted to longer baselines, which is a good thing, because then you can measure more things that are closer to the black hole. So for example, it's easier to measure. It's easier to measure with a larger n. It's easier to measure the innermost stable orbit. If n is smaller, then the peak is happening very far away from the black hole. So basically, when you over-resolve this region, you completely lose sensitivity to things close to the black hole. And it is kind of sensitive if it's 3 over 2 or 5 over 2 or 1 over 2.
This is exactly for what n?
Oh, this is for Sakura Sunaev. I forget exactly what n was. Sorry, I think it's 3 or 3 over 2. 3 over 4. Okay, good. Yeah. I put in I had the Sakura Sunaev, then I remember that anyway, yeah, it's the Sakura Sunaev. It's n over 4. There should be n over 4 there.
Okay, so let's thank Marius again for the nice talk. Right, so we're ready for the second talk, and we also kind of switch gears now. So this is kind of a general idea, like, I mean, the organization of this workshop, like to kind of mix different subjects together so that like everybody can like hear a little bit of other subjects that they're not necessarily working on. So we're very happy now to have Stavros Mougekakos, who is going to tell us about QFT-based methods for classical gravity. So please.
So good morning, everybody. So before starting, I would like to take my turn in thanking the organizers for putting together this nice workshop and also for the invitation to speak. So, okay, as the title suggests, I will speak about some methods which are inspired by QFT, quantum field theory, and they are used for classical gravity. So it's like a relatively recent subfield that has emerged in the field of scattering amplitudes and effective field theories. So, okay, I will try to split the talk into three parts. So the first is like a motivation of how and why we use the stuff. Secondly, I will try to give some rough sketch of how these work. And finally, I will refer to these two recent works that are trying to extend these into a new expansion that I will talk about. So, okay, let's go. So I suppose most of you are familiar with the story of the detection of gravitational waves. So this happened roughly 10 years ago. In practice, we entered this so-called gravitational wave era after the observation, due to the fact that now we have the chance to do multi-messenger astronomy, to have an observational window on strong gravity, to search for exotic objects, new physics, and anyway, whatever one wants to do with these observations. The important point is that all this story relies heavily on how you theoretically predict your signals, because the signal is very weak. It has a lot of noise. So all the detection lies on the theoretical template, the gravitational waveforms that we call, in order to identify and extract the physics out of that. So in practice, this story brings us to the accurate prediction and the two-body problem in gravity eventually. So what we want to do is to solve the two-body problem in gravity, construct the waveforms, and use them to do this masked filtering in order to identify the signal. So let's see what is the typical event. This is a typical event that we are observing. So they are comprised by these three phases, the in-spiral, the merger, and the ring down. So what I'm going to talk about mainly is the in-spiral, which can be subject to an analytic treatment, because there you can use perturbation theory. The merger is solely treated in numerical relativity. It's a very violent event. And in the ring down, also numerical relativity and black hole perturbation theory can be used. But okay, let's focus on the in-spiral phase, because analytic treatment is what I want to talk about. So let's see. Here I'm trying to sketch the general pipeline that one uses when they want to construct these waveform templates. So besides numerical relativity, that is a very core method that is being used, other methods which are purely analytical can be used in order to extract dynamics from there, inform this effective one-body formalism, the so-called effective one-body formalism, to construct the templates. So in practice, we will forget about the left bottom side of the slide, and we will focus on these three perturbative expansions that are being used. So these are the main three. So let's take them one by one. The post-Newtonian is, let's say, the most straightforward. One expands in the coupling coefficient of gravity and the V over C. This is a double expansion, but of course for bound systems they are connected through the virial theorem. The point is that you have this double expansion. Now in the post-Minkowskian, one treats the problem relativistically. So you have only, it's a weak field expansion, so you have only expansion in G, but not in V over C. And in the cell force expansion, here we adopt a different point of view. So it's not a weak field expansion. It's an expansion over the mass ratio. And in principle, it's used for extreme mass ratio in spirals. So, okay, let's see the connections between all these expansions. Let's focus on the post-Minkowskian and the post-Newtonian. So, as I told you, one can see the relation between these two expansions in this way. We see that if you take and expand the 1 p.m. order, the so-called 1, this is a summation of the velocity contribution. So in a sense, if you have the 1 p.m., you have infinite amount of terms of information that contribute to relative pn orders, increasing, and to infinite order. So we have to understand it in this way. The pm resums, in a sense, the pn. Of course, this is a rough sketch. It's not that it works exactly like that, but just to have a power counting idea. So this is the way these things are connected. But there is also a similar connection between the Selfors and the post-Minkowskian, which goes like that. So the zero Selfors is let's say, the geodesic motion. And indeed, one can understand in a similar way as before that if you expand the geodesic motion, you recover again infinite amount of terms in the post-Minkowskian expansion. And indeed, here the scaling is even better because you can get up to 2 p.m. completely from geodesic motion and also for free the rest of the terms. So if you symmetrize again between the two bodies, you get the complete answer. So what I want you to keep from here, from the previous slide, it's that all these perturbative expansions have a relative connection between them, and you can transfer information from one to the other. So it's like a synergetic way to work and inform and cross-check also. So let's see the methods that one can use. So in practice, I decide to group in two parts. One is the GR perturbation. So let's refer to them as more traditional methods because mainly because they pre-existed, to be fair. So here there has been a lot of work in all of these types of expansions. But more recently, there's this effective field theory and scattering amplitudes approach that, let's dub it, modern methods, in contrary, which has tried to, with these techniques, we have tried to address these expansions. In practice, up to today, we have been addressing the post-Newtonian and the post-Minkowskian, and they come in chronological order. So, let's say in 2004 around, the post-Newtonian expansion was treated using these kind of methods, and around 2015, so 10 years later, also we started applying in the post-Minkowskian, and now 10 years from then have passed. So in practice, it's time to consider how one can use the Selfors if we want to be consistent with the calendar. So I will try to roughly sketch what are these, how these things work. So bear with me a bit if you're not familiar. So here I will focus on wordline approaches. So there's a sub-distinction in these modern methods that one can use wordline methods or purely QFT methods. I will not bother with all this because it's a complication. Just keep in mind that there's also another way to do this stuff, but I will focus on one branch. So the typical event looks something like that. And we know that there's an hierarchy of scales. So we have three scales in the problem. So we have the Schwarzschild radius, the orbital separation, and the gravitational wavelength. And these are highly separated in the inspiral phase. So in practice, this kind of a setup screams for an EFT description because we can split the regions of the problem in three independent ones. And by matching each region, we can recover the whole solution, but we can treat them independently up to some point. So this is what we do. This is the idea. In practice, we focus on each scale at once, and we solve independently, and then match. Now, if we want to split it into some points, so the Schwarzschild radius scale of the problem is, let's say, the most resolved and trivial in a sense, because we take the point-particle approximation. So we assume that we are far away, which we are, and we see the black holes effectively as point particles. And using the symmetries of general relativity, we can write down an effective action for this point particle, where here we have the minimal coupling for a point particle with spin, and then you can compensate with higher derivative interactions and non-minimal couplings to describe your finite size effects, and so on and so forth, absorption and whatever one wants to describe. Secondly, we are treating also general relativity, the bulk theory, let's say, where we embed the two-point particles as an effective field theory as well, where the first leading order is Einstein-Hilbert, and then, of course, one could compensate with higher derivative interactions. Here, the point, in practice, we are using general relativity, to be fair, and the rest we kind of not deal with them yet. But the point is that this is a generic and adaptable setup to consider also modifications of GR. Finally, since we are working with amplitudes, we are used to working with amplitudes in flat space. In practice, we are doing weak field approximation. So we expand the metric around Minkowski, and we quantize effectively the perturbations, the gravitons. After doing this setup, we want to extract this effective theory. So we write down our Feynman rules, and we compute loop diagrams. So I will show you in a bit why we need these loops. The point is that the whole computation comes down to constructing multi-loop Feynman integrals and solving them. Finally, since the problem can be, it's kind of adjusted, so you have to specify your kinematical region. In the PM expansion, for example, in practice you are dealing with a scattering problem, so there is an extra point that the scattering problem is not something that we are observing as an event. So we need to translate this information to the bound problem, and this is what is being done with mapping between these kinematic regions of bound and scattering systems. I will not talk about that, but have in mind that we also have such tools. In very practical sense, we have on the left-hand side our effective action, and here on the right-hand side we have Einstein-Hilbert, okay, the gauge fixing as always, and the point particle. And we are integrating out the graviton. This is how we extract the effective theory of these point particles interacting. In the language of word-line approaches, integrating out gravitons is equivalent to focusing on the classical physics is equivalent to not taking into account closed graviton loops. So here it's just a rough sketch again up to g cubed of the diagrams that appear, because this is how in practice we are integrating out the gravitons. So this is the tree level, this is one loop in a sense, one loop because it gives a one loop Feynman integral, and then these are two loop stuff that give g cubed, so it's like an L plus 1 the counting. So how much time do I have? I have a lot. Nice. Okay. So I spoke before about the cell force, which is a third, let's say, expansion, and that it's kind of time to start thinking how to apply these methods in the cell force. So at least in my opinion, in order to do that, it's necessary first to have a self-consistent framework for the Schwarzschild. I mean, this is the simplest thing one can do, one can think of, and we want to address this, the Schwarzschild metric, and recovering it from these techniques, just to make sure that we do everything correctly. So it's a strong cross-check, at least that we don't do wrong stuff. But in general, the idea of SFEFT has also been initiated by these groups. And it's something that I think that in the future it's a promising avenue. So let's go and focus on what we did in these two works concerning the Schwarzschild metric. So here we're going to go into the more practical sense, so I hope you will get a better idea. So we have on the one, let's think of it in this way. We have on the one side the GREFT description of general relativity, and on the other hand the truth, the real theory, the general relativity. And we want to match the two solutions. We know from GR what is going on, so it's fine. So we want to compute it from here. And the equivalence of these two descriptions, of course, is up to the choice of degrees of freedom that we are comparing, we are matching, and the choice of the gauge. So we're going to use the harmonic gauge because it's convenient for us, and we're going to make this expansion, as I told you before, for the metric tensor. The expectation, which was already there from 1974, so it's a pretty old idea in a sense, is that if you go and compute the graviton emission, the off-cell graviton emission from, okay, here it's a scalar field, but also one can work in word lines and just have a local source. And here this blob represents the loop structure that you can include. The more loops you go, the higher g to the n plus 1 terms you will get in the metric. So in a sense, you know the result, and you want to make sure that you get it from your techniques. And it's a matter of loop orders that you compute. So the expectation is this. Go start adding loops, and you get the terms of the metric order by order in G. The problem is that it's not that trivial in the end of the day. Actually, it was much more complicated than expected. And indeed, in this work here, like 4 years ago, we tried to do this, at least to investigate how this computation indeed scales. And there are two main problems when dealing with this off-cell quantity. So the first is that you have intermediate UV divergences that come from your description of the point particle. And they are intermediate in the sense that we know that they are a gauge feature, but indeed, in order to be self-consistent in between the computation, you need to take them into account. And this is an infinite hour of these non-minimal couplings that you need to add to regularize your stress tensor and your subsequent metric. The second is that there is no algorithm for higher loops, so we went up to 3 loops, but going higher it's a bit of a pain. And this is connected with a known fact that when you go and treat GR in this way and you expand, the Feynman rules that you get for the self-interactions of the gravitons are super annoying and very complicated. But the most important point is that they go up to infinite order of self-interaction. So you can have as many gravitons self-interacting out of there. And this is, in practice, what is obscuring you from creating an algorithm to go from one loop to the other. Because we said that we want to do something to all orders in G. So if you want to generalize, you need a recursive way to build your loop expansion. So we took a step back. It took some time intermediately. But in the end, we managed to succeed in this idea. So let's see. We take this for granted this way, and indeed, in these amplitude descriptions, this is the way that people do stuff. But if you remember before, in the EFT, in practice, you are integrating out these degrees of freedom. So in practice, why should you care how you parameterize your graviton? You shouldn't care. You should pick the most efficient way to do this. And indeed, this is what we figured out in the end of the day. So inspired by this paper by Chung and Remen, which for here, this is not the title, but the cubic formulation of GREFT is the point of the paper, the part of the paper that we are using. So what happens here? One can write down the Einstein-Hilbert action with respect to 2 degrees of freedom. So one, the Gothic metric. So GR people have been using the Gothic metric as a description. It's just that in amplitudes we didn't want to do that because it seemed more complicated. Finally, it seems that it's even less complicated. And the lesson to take here is we should pay more attention to what other people do sometimes. So we use as a degree of freedom the Gothic metric, the inverse Gothic metric. And then we are also introducing this extra auxiliary field which is connected to the connection. It seems unorthodox, but it's necessary in order to rewrite exactly the Einstein-Hilbert action with respect to only cubic interactions. And in a moment we will see why the cubic interactions is important. So having this, okay, this formulation looks a bit like the Palatini formalism for those who work on that. But for us, the point is that we want to constrain to the 3-point. Again, okay, we have to make a choice of gauge. Here, for the people that are a bit more familiar, they know that the harmonic gauge is not a unique choice of gauge. It's up to an integration constant. And this is, in technical terms, this is super important in the end of the computation. But okay, probably we'll avoid this discussion unless somebody asks. Anyway, so we take this formulation of GR and we couple it to the word line as before. We write them with respect to our degrees of freedom, blah, blah, blah. The point is that we want to compute these currents to all orders in G. Indeed, we know that these depend on a single multi-loop master integral. It's a multi-loop bubble in the end of the day. And so there's a correspondence of the simplicity of the Schwarzschild solution to the simplicity of the amplitude side computation. Here, we have a very simple solution on the Schwarzschild side, and on the other hand, we have a multi-loop bubble, which is pretty simple in Feynman integral language. So we can parameterize our currents, which are like the Fourier transforms of the fields here, with respect to 8 form factors. 7 of them are independent in reality, but we don't make this. We don't use this assumption, but we prove it explicitly out of the computation. So here, okay, let's explain the notation. This n is the order of G that appears. So all these depend on this rho parameter, which is defined here, and in practice it's counting the powers of G, and it depends on the momenta, on the outgoing momenta of cell. So the game in practice after this parameterization is to figure out these form factors to any order in n, put them, replace them, resum them, and see if we've got the Schwarzschild metric to any order. Okay, a bit of the diagrammatics to make a sense of this story. So the Feynman rules here are the following. We have the the Gothic graviton coupled to the world line. So here this is the trivial part. And we have managed to constrain, but just by introducing, and here I would like to take a minute to appreciate that. We have started from a theory that we have 1 degree of freedom and we have infinite amount of self-interactions. And we have rewritten in a way that we have 2 degrees of freedom with 3 interactions. So it's a super simple formulation. And this is the reason why we can generalize to all orders. So let's take an example of the G to the cubed, which is like a 2 loop. One can take the sum of these diagrams that needs to compute for the G cubed and can recognize a substructure here, which can be written with respect to the previous order. I suppose you understand where the story goes. Seeing that there is a substructure, we can write with respect to the previous order, and we can generalize this as an iterative structure to all orders in the loop expansion. So we are computing recursively each loop, and we are recycling this information. And indeed, this is the only way to get something to all orders. You need to find the way to build it recursively. Now let's see why this cannot be done with if you have the higher point interactions. If you had the 4 point, for example, here, you should add also the diagram that has here the 1 leg outgoing and 4 legs here, 3 legs here connecting to the world lines. Now this would be a new topology. And it cannot be written with respect to the previous one. So at each order, you would have a new topology that enters that you cannot recognize as a structure from before. So this is the point why you need to have a finite. It's like combinatorics for the binary trees. It's not something super special. Okay, we have this iterative structure to all orders. It comes due to these 3-point interactions. And indeed, we can write down a recursion relation. This we computed. It's not up to, it doesn't come from an assumption or anything. We can write down recursion relations for all these form factors. These are solvable at d equals 4 exactly, and there is no UV divergence. Now, furthermore, I mean, we have this closed form at any order n, so you just plug them back in as I promised, you resum them, and you get explicitly the Schwarzschild solution. Okay, I will see later if I will return to this point. Okay, I have time. I will say it now. So the GREFT computation picks some gauge. As I told you before, the harmonic gauge is non-unique. It depends on an integration constant that you have because it's defined by a differential equation, the condition. So if you put this integration constant to 0, then you land up to what you find in Wikipedia for the harmonic gauge. But in practice, if you don't set this to 0, you don't have a non-invertible form of the transformation. And the problem there is that if you don't have the invertible form, you cannot find even what you are looking for on the GREFT side. So it's subtle what integration constant your EFT computation picks. And in practice, the previous computation that I referred to, that we were having the UV divergence, etc., was internally picking another integration constant, and this is why we're getting these UV divergences. So in this formulation, in practice, you solve both problems at once. You have the recursive form, you avoid the UV divergences, you can use this stuff to go higher in the SF in principle, which at least for now we haven't done it. But what I want to discuss now is, okay, we got the metric, but we want to solve the complete problem of the geodesic motion, so we want to get the geodesic equation in the end of the day, which is not identical in our case, due to what, okay, I will explain why it's not identical. Let's see the setup first. So we want to build some cell force effective field theory, or whatever name we will give it. So how this happens? Exactly as in the PM. I mean, it's not something new. Again, we want to extract an effective action from the original theory that contains here H is for heavy particle, capital M is the mass, and the light particle will come with a small mass here, you will see. So we write down the complete theory. We want to integrate now both the auxiliary field and the Gothic graviton to get the effective action. So we will do this again in diagrams. The only difference, and the reason why we will name it in another way, is that we will presuppose an expansion in powers of small over big M. So here we have the leading order, which is just in the rest frame of the big the big compact object. It doesn't necessarily need to be a black hole. The big compact object will just be there in the proper frame, and then we will have an effective action that we will need to compute from the diagrams by integrating out, that will scale with powers of m over n. The L0, for example, you see that it's going to be proportional to small m, and so on and so forth. Also, in order to set up this expansion, we need to self-force expand the trajectories as well that we were going to iterate later. Anyway, we just do this again in powers of m over m, and you see that the leading order term here, it's just the proper time. It depends on the proper time. For the light particle, the leading order equations of motion is the geodesic motion. In practice, I want to show that how we get the equations of motion for this from this effective L0 action. Now, what is the problem here? I lied a bit in the sense that before in the metric computation, I showed you only this interaction of the Gothic graviton, but this is not complete. Due to the expansion we do, we exchange the complexity and we have arbitrary amount of gravitons emitted directly from the word line. We don't have, in the theory, a direct coupling of the word line with the auxiliary field, but we have multi-graviton vertices. So in order to compute this L0, we need to compute this infinite amount of diagrams. They are fun diagrams, they scale like that. Additionally, so we have one is that we have infinite diagrams. The second problem is that here the below couplings, the square couplings, here these are the big mass couplings, insertions, and on the top are the small body insertions. So you see even from here you understand that each of these contains a power of small m, so just this is the way that the power counting works. So at one SF, one would require to have two insertions of the small mass on top. Anyway, this is for generalizations. But here the square, in practice, is a sum over all the orders of the dressed graviton. So we have dressed propagators that we computed before. This is the metric. And all these emissions here are the dressed stuff. So we have a second infinity that we need to deal with, which is that we have put it here secretly because it's going to be a mess if we write everything. So how can we do this computation? I mean, in the end of the day, it's not very, I mean, I present it here, so we managed to do it, so it's not a spoiler, but I will try to explain a bit how we do this. So we want to split into two parts the computation, where we define a tensor here, tau capital, which is in practice it's trivial. It's like the contractions from the Feynman rules here. It doesn't contain any momentum dependence. And the important part is this calligraphic I, which is coming from actual loop integrations. So we don't care for that now. Let's say that we have a control over it. I mean, in the end of the day, you can't control it. It's just combinatorics. And see here what happens. So here one starts. Okay, I know the notation is a bit compact, but the point is that we have a Fourier transform over the exchange momentum k, and we have an infinite amount of loops that needs to be integrated, because the more legs here, the more loops you have. And this has to be integrated. The argument, the integrand, is this series over all of these n1 to nl, where L is the amount of the propagators here. So it's a bit messy. The trick here is to use, so we start from a Fourier plus infinite loops, and by using just the integral representation of the delta function, we see that this decouples all the loops. So you end up with an infinite amount of decoupled Fourier transforms. So this can be put under control. In a more simple language, the point here is that the interplay between the Fourier transforms and the loop integrations, the flexibility that we have in this language to play between them simplifies and trivializes a computation that, if you see it from before, I mean, it's impossible. You cannot even do it in the computer. You cannot put it in generality. So we get a closed form for that. In the end of the day, one can compute it, write it down with respect to this parameter, which is gm over x, over the distance of the small from the big. And this is just, we write down with respect to this L. So putting everything together, we can again write a recursion relation of this contraction, of this sum, that we can put it under control as I showed you. And this resums, boom, to the geodesic equation. So one can say that we didn't do anything. We just rediscovered America because we just landed on what we should have started from. The point is that even though this is trivial from the GR perspective, because you know that you should start from there, from the EFT point of view, it's highly non-trivial, as I showed you. And the point is that if you want to exploit these techniques to go higher, to higher orders in DSF, you need to have control over this stuff. It's a bit dangerous to assume that the techniques give you what you're expecting. You need to show that they are giving exactly what you're expecting. So, at least in my opinion, it's a crucial stepping stone to go beyond zero SF order. So with this, I will close. So just some concluding points. So, seeing the classical GR through the lens of QFT and the techniques and tricks. So, the first point that in practice has initiated this whole program is that we can efficiently exploit the knowledge that we already have from particle physics. So people have been doing this stuff for many years, and they know how to compute Feynman integrals, to do diagrammatic organization, to use to regularize their divergences, etc. These are stuff that come also in the classical GR computation. So in practice, why not just copy what we have already done and apply it somewhere else? I mean, this is the smartest thing to do and the most lazy, but it's very efficient here. Secondly, there is an example that I removed due to time, but okay, I can tell you just that there are some, there is a result for the case of the gravitational Bremsstrahlung that using the techniques, the traditional techniques, one cannot land to a closed analytic form. So there is a case that reformulating the problem with these techniques gives you a result that you cannot even compute. So up to now, we have reproducing, let's say, results that have been already computed with GR. But the point is, okay, to justify yourself and your existence, you need to do something novel. And this is a concrete example of a novel computation, the case of Bremsstrahlung. Unfortunately, we didn't have time. So the message here is that we can possibly overcome shortcomings by reformulating in another language the same problem. It's easily applicable to GR modifications. I think this is self-explanatory. And up to now, we have done well in the PN and the PM, but we need to extend also to SF. It's, as I told you, 10 years past. Now, probably we have to start doing it. In the setup that I showed you with the cubic story, the diagrammatics to going to one SF are very clean. It's very specific what you have to do. Of course, the extent of analytic control of this computation is up to debate, and one needs to do it in order to understand exactly at what extent it goes. But from this organization of the computation, at least you can split it into parts and see which part you have analytic control, which, okay, in the end of the day, you will probably need some numerics, which are already used in the SF anyway. The final point is that this is in principle non-perturbative approach by resumming the flat background the interactions, which is EFT based, can be used for other questions regarding black holes. So one can investigate, and this has been done in it has been initiated in other papers for love numbers and their vanishing in D = 4, for possibly long-range quantum contributions that one can have, for higher dimensional black holes, and anyway, whatever one thinks about and can be applied. So, okay, with this I will finish.
Thanks, Stavros. So are there any questions?
Please go to slide number 16.
Of course.
Yeah. So you mentioned, I guess it's in 4, that essentially the method that I applied from EFT and amplitudes describes scattering.
Yes.
We are interested in the Bound motion, and you also have this map over there. But to my understanding, this is an incomplete story. This fails.
It is.
At some, I guess, loop order or post-Minkowskian order. And yes, I was curious what is the status of this, I think, very important piece of map that needs to be understood for these methods to really apply to the observations, the gravitational wave observations.
Okay, great question. Thank you. So, okay, here I'm trying to do some rough sketch, so I'm hiding some some secrets of the community, but now they have been exposed. So, for the let's start from the from the first part. So for the PN, these techniques are used, and you can land yourself on the bound problem directly. You know that. I tell it for the rest of the audience to follow it. Now for the PM, that we are doing relativistic approach. We are in practice working in the scattering kinematic regime. This is where we start from, and then we struggle to reshape this information in a way that it's relevant for the bound problem, and this is what these mappings refer to. Indeed, these maps, when you don't have the radiation, because this is the point, the mapping between the hyperbola and the ellipse is a geometric mapping. This B2B maps is a geometric in origin, and the reason why it fails is that when you take the radiation reaction in the problems that enters at some order in perturbation theory, you spoil this geometric map. The status now is that this is still unresolved, as you know, but I think that the most conservative thing that I can say is that one can, again, bring pieces of the computation, for example, the conservative parts, keep these as a mapping, and deal with the rest of the problem of the radiation separately. This is one take. The other is to try to build a complete map of the both conservative radiation reaction terms and try to map it. But this is, I mean, this is work in the doing, and I'm not a specialist, I would say, in this.
But does your self-force approach also
It has the same problems.
has the same problem?
Yes, you cannot avoid these problems because the map is the origin of the map is the geometry of the problem that you're just mapping through analytic continuation a hyperbola with an ellipse. It's not something like super crazy.
Yeah. So I have prepared. Okay, I'll start with the general one. For the self force, this is what go from zero self force to one self force. The biggest problem is that when you back react to the Vedic, the problem is distributional because that's the geodesic is around a specific trajectory that Einstein equations are nonlinear. They get perfect distribution, and they spend 10, 15 years resolving it.
Mhm.
So does this new methodology enlighten how to resolve this substitution?
Okay, first I have to say that we haven't yet done one SF, so I wouldn't want to sell that we have it and we don't say it. Now in the core, okay, so the reason why these techniques became relevant, there is a secret in the other communities that there was an issue in the handling with the regularizations. So they were using Hadamard, for example, in the PN. What the main thing that these techniques offered is a clean setup to treat the divergences, so DIMREG. Something analogous happens with the SF computations. So, of course, I'm not expecting that we can solve the geodesic equation completely. And, I mean, we have the same equation, the same problems happen there. But the goal is to try to isolate the part that gives you these regularization issues that don't come from the iteration of the geodesic equation. They come from the source. So it comes from the dynamical field and not the motion. And in this sense, if we can isolate that part and understand better how you regulate this, if it can be naturally regulated in DIMREG, then this would already be a big gain, in my opinion. So in a sense, we are splitting the problem in two parts. One is the integrand that you have, and we want to simplify this story. And this actually also is helpful for the PM, because then you can use it as a reorganization of the PM and re-expand, etc. But we want to isolate the part of the integrand. And then again, indeed, when considering the background motion, the iteration of that, then probably we cannot do something better than numerics. So divergence is the point that we are aiming for. No.
I wanted to ask something related to this main goal. You mentioned many times that you want to reproduce a Schwarzschild black hole, and you seem to have succeeded in some sense. But I was wondering, at what point, if you wanted to reproduce a Kerr black hole, what would have been any different? That's one question. And the second is a bit of curiosity. You showed us some recursive relation, which is highly nonlinear. Can you just, yeah, just that's the solution. How you solve that?
So it's not highly nonlinear, first of all. Uh, it groups together, it groups terms, so it's several terms in this matrix are diagonal, so it's not that nonlinear as it looks. Maybe the presentation is not very enlightening, but I mean, okay, I can tell the easy one. So with the paper, there is a mathematical file that comes there, and you can press Shift Enter, and you get the solution. There are no UV. Okay, first of all, we don't expect UV. Yes, sorry, I will go to the care. Okay, the care. Okay, the second part is that this is an exact solution. There is no thing, so it is indeed not kind of solution, it is the solution. The second point is that the care is highly more complicated due to two reasons. Here we have a single scale problem, so we have only G. When you include care, you have also the spin, so you have a double expansion. This makes it a more tricky story. So this is the simplest. No, we would not. We would need to also treat perturbatively the spin, which is what happens in PM and PN. Unless one can figure out, I mean, there are works in the spin also that exponentiate and can resum, etc. But in a world like, so there are ideas there. But in the end of the day, it seems that you should expand also a spin, so resum two scales, and the integrands become a bit more complicated, and the extent where you can deal with them, it's obscure to me for now. An easier question would be, for example, Reisner-Nordstrom, that you have two scales, but you don't have the ugly integrands, if this can treat it.
So I think the question is what question?
Just maybe naive question. Okay, I don't really understand what is the motivation to calculate something orders of Z. Maybe as naively, okay, conceptually I can see. Practically, to see there is an expansion of one order quantity. The second order is much more logical than the first one, and then goes like, I think I'll be happy just to have a couple of let me say, orders of blank, and that's it. Because is this any phenomenon, or let me say something where one can, I mean, this let me say, all order calculation can be tested for the accuracy of the calculation will match, let me say, the accuracy of the calculation.
Can I answer? Yes, MRIs. In MRIs, you do these computations. They are relevant. I mean, so there are several studies that show how even the 1SF outperforms very high order of PM expansions. So in the case of MRIs, you are dealing with the exact background space-time, which is all order in G, and you are computing the motion of the small there. And MRIs, not only that you need all order in G to do MRIs, but it seems that MRIs, this SF, perform very well, even in relatively very smaller mass ratios than expected in the beginning, if you symmetrize between the two masses, etc. So the all order in G, it's something that is not irrelevant from a practical point of view, because for LISA and for MRIs, we will have to use this setup. This is actually what is being used. And from the theoretical, it's for fun, as you said.
So I think we should keep the rest of the questions like for the break. So we're a little bit late, so I think we should move first. Thanks, Stavros, again. And let's move to the next speaker. Now to the next speaker. So the next speaker is Antonia Paraskivapoulou, who is going to tell us about reflections on an M-theoretic emergence proposal.
Thank you very much for the introduction. And of course, let me join the rest of the speakers in thanking the organizers for putting together this very nice workshop once again. And of course, for giving me the opportunity to talk about my work on the emergence proposal. Actually, I am cheating a bit. I am using the title of a recent review article that we published, summarizing our current understanding of this topic. But I will actually be focusing on the results of a relatively recent publication related to this, with the same collaborators, my supervisor, Ralph Blumenhagen, Niccolò Cribiori, and Alexander Gligovic. But before I go into the specifics of what we were interested in, let me take a step back and introduce the general framework, which is the Swampland program. I have actually seen there's more Swampland talks coming up, so I think it will be useful for all of us to be on the same page. So the goal of the Swampland program is to distinguish between those effective field theories which cannot admit a viable UV completion into quantum gravity theories, and which are what we call the Swampland, and those theories which indeed could lead to a consistent formulation of quantum gravity. And in order to distinguish between the two types of effective descriptions, our tools are a set of conjectures motivated mainly, but I should stress, not exclusively by string theory. In fact, there's ongoing attempts to try to collect more evidence from black hole physics, for example, to support these conjectures. In any case, we have a very large number of conjectures, an ever-growing one perhaps, and eventually I will be focusing on a more peculiar statement within this set of conjectures, which is the emergence proposal. But how do Swampland arguments generally look like? Now, one of the main statements of the Swampland program is the Swampland distance conjecture, which is actually what kick-started this entire program. This conjecture is a statement about the moduli space of string compactifications. Now, as you know, string theory is a 10-dimensional theory, so in order to make contact with our 4-dimensional world, we need to hide away these additional dimensions by compactifying. In doing so, we get a number of scalar fields, the moduli fields, whose vacuum expectation values roughly parameterize what we call the moduli space. And what this conjecture is telling you is that if you transverse across an infinite geodesic distance in this moduli space, you will always encounter towers of states becoming light with the Planck scale. And effectively, what this tells you is that your EFT is breaking down, and what you need to understand is actually a dual description, which becomes relevant at this limit. And despite all of the various complicated string setups that you can consider, it has been conjectured that in any case, all of these limits fall under two categories. Either you have a decompactification, one or more of your dimensions are again becoming very large, in which case the lightest tower is that of Kaluza-Klein modes, momentum modes, roughly speaking. Or what is happening is that you're probing an emergent string limit, in which case your lightest tower is a tower of light states coming at the same energy scale as, again, some Kaluza-Klein tower. And this has been going under the name of the emergent string conjecture and has so far been thoroughly tested in a series of string compactification setups. In fact, if I'm not wrong, there was even a paper out today further extending these results and supporting them. And because of these statements, usually in the Swampland program, it is precisely such infinite corners that we are focusing on, exactly because we get all of these new light states and we believe there's new information. And one generic property of all of these effective descriptions is that the effective cutoff of our theory is not given by the d-dimensional Planck scale, which is the energy scale that you would naively associate with a d-dimensional description of gravity, but by a much lower scale due to the number of light states that are appearing in such limits, which I'm denoting here by NSP, which has been called the species scale by Guy et Valli. And in fact, properly defining the species scale in any theory and distinguishing it from any other possible characteristic energy scale that might come up is still an area of active investigation within the Swampland program. But let me note here that it has been suggested, as one might naturally expect from a field theoretic intuition, that we should consider the species scale as the energy scale. An appropriate power thereof is suppressing higher curvature corrections that we get to our familiar Einstein-Hilbert term. And in fact, it is precisely such a higher curvature correction that I'm eventually going to be focusing on today. In any case, apart from this lowering of the species scale, despite our extended investigations of the swampland program and the various qualitative effects that come into play for effective descriptions, not much is known about the quantitative effects of the appearance of these light states. And it is precisely this gap that the emergence proposal was initially trying to bridge. Now, in its original formulation, or what you might find in the literature as its strong formulation, what it was claiming was that the dynamics for all fields are emergent in the low energy limit by integrating out states down from some ultraviolet scale below the species scale. Now, of course, having just heard the distance conjecture, we understand why we're talking about towers of states, exactly because we usually have in mind such an infinite distance limit. And knowing also the definition of the species scale, we understand why naturally one associates this energy scale lambda to the species scale itself. Initially, by dynamics here, what people had in mind was just the kinetic terms, but actually there was also more evidence about other couplings being emergent, so one could even extrapolate this notion and expect that the entire low energy effective action should arise as such a quantum effect coming from an integrating out procedure. In any case, calculating just loop corrections following this mindset is probably very natural to anyone familiar with particle physics. Say we have one modulus field, we can expand its mass around its vacuum expectation value, and then at one loop we will get very simple diagrams. We can apply our usual renormalization techniques and calculate, for example, the one loop correction to the field metric. In principle, initially, people were focusing a lot on this effective approximation of the emergence proposal, and there were some very interesting results in this direction. I should also note that there have been some very interesting results connecting the emergence proposal with topological strings. However, this is not the mindset that we had. We were curious to try to understand where the initial formulation of the emergence proposal could actually come into effect. Where could we expect that the entire couplings would be arising as an integrating out procedure? Now, precisely taking under consideration the fact that full results seem to not be available in emergent string or some decompactification limits where light strings are still present, we were naturally led to an M-theoretic refinement of the emergence proposal. Now, M-theory is an 11-dimensional theory for which we don't know too much, but it is believed to be the underlying theory of all our familiar 10-dimensional string theories. And usually you can understand it as the strong coupling limit of our more familiar type 2A string theory. So what our refinement suggests is that in the M-theory limit, where the 11th radius is considered to be large, which if you apply the duality maps is an equivalent to just saying that this is a strongly coupled limit of type 2A, and which we were approaching by keeping the d-dimensional Planck scale fixed, a perturbative quantum gravity theory arises whose low energy effective description is emerging in the sense of coming by integrating out the full infinite towers of states whose mass scale is parametrically not larger than our effective cutoff in that limit, our species scale, which in this case of a decompactification is just the 11th-dimensional Planck scale. And now, if you're familiar with the vocabulary of all of these theories, you can just sit down and do a bit of bookkeeping, analyze the limit, see what are the light states that are relevant in the theory, and it is obvious that since the 11th direction is large, we cannot expect to get light states by wrapping our extended object, our membranes, around this large direction. So indeed, the spectrum of light states only includes transversely wrapped M2 and M5 branes, possibly also carrying Kaluza-Klein momentum along any compact direction potentially present. Or, if you're more familiar with the type 2A vocabulary, this just means that the light states are just, the light particle states are just wrapped D2 branes, NS5 branes, D0 branes, and possibly any Kaluza-Klein momentum arising. And let me just comment that so far, I have just motivated this from a pure swampland point of view, but morally, one can even spot some similarities between this approach and independent approaches to formulate M-theory, such as the BFSS matrix model. But in any case, if we leave this debate aside, I have made a statement. We can at least check the limit, calculate their species scale, but the question is, can we really test it by actually confirming that we can completely calculate some effective coupling? And in order to do this, as I have already spoiled for you, we looked at a particular higher curvature coupling, namely an R to the 4 term, by considering the simplest compactification setup that you can think of. We were just assuming that we are compactifying our M theory on a k plus 1 dimensional torus. I'm referring to it as plus 1 because I'm distinguishing the 11th direction, which I'm taking to be large, from the rest of the k compact directions, which are not scaling in M theory units. And a motivation to look at this particular coupling, rather than just any other coupling, apart from the fact that it has already been linked to the species scale, is that it's a 1/2 ppm saturated quantity, which means that supersymmetry protects it against receiving perturbative corrections beyond one loop, and that it was already, to some extent, calculated in a very interesting work of Greenwood, Perle, and Van Hove, and was seen to be arising precisely by an integrating out procedure, which is exactly what we have in mind as emergence. However, what they were getting was a Schwinger-like integral where the light states that were being integrated out were just the Kaluza-Klein modes of the theory. And just to warn you, these expressions will be UV divergent. So whenever I'm giving you such an expression, if I want you to be able to expand it and actually track down the various contributions, I also need to provide an appropriate regularization method. The authors of that original paper were actually performing a Poisson resummation over all of the integers that are being summed over, but they still left them with a formally infinite constant term that needed to be indirectly fixed by applying, for example, T-duality. But I'm guessing a natural question at this step is, what more can we learn? If this has been calculated, why are we interested? Well, as you will see, there were some pieces of the puzzle missing. So first of all, if you go back to our emergence proposal, you will realize that there is no particular motivation to only look at the Kaluza-Klein modes here. They're only a subset of the light states of the theory. So what we suggest is that one should better extend the original ansatz of Greenwood, Perle, and Van Hove to include the entire spectrum of light states allowed by the supersymmetry restrictions of the theory. So here I am now no longer integrating out only the Kaluza-Klein modes, the momentum modes, but also any configuration of D2 and NS5 branes, which is allowed by my supersymmetry restrictions. And additionally, we were also using a different regularization scheme, which we actually developed in an earlier work with the same collaborators in the context of calculating the prepotential of the resolved conifold, which consists of 3 steps. First of all, we started by performing the integrations, introducing some arbitrary UV regulator. We then minimally subtracted any divergences that were only related to this arbitrary regulator. And then, as a final step, we are performing a zeta function regularization of the infinite summations appearing. Now, notice that if we were not really integrating out the infinite towers available, the final step would not be possible for us. We would be cutting off the towers at some energy scale, and then at the final step, this would not be possible. But how does this practically look like? Well, in 10 dimensions, we only have the 11th direction being compact, so we are not much further away than Greenwood, Perle, and Van Hove. We cannot construct more light particle states. However, it is a non-trivial consistency check that also our method gives rise to the same correct tree-level term as their computation. However, in our case, there is no suspicious infinite constant that needs to be kept. And the picture remains completely identical also in 9 dimensions. Once again, we do not have enough compact directions so that we can create more light particle states, but indeed we can recover the complete tree level and instanton contributions to this coupling, same as Greenwood, Perle, Van Hove, again with no infinite term arising, no additional infinite term arising. But things become truly interesting when you reach 8 dimensions. Now we have 3 compact directions, and we have 2 of them not blowing up and are available for us to wrap our extended objects and create light particles. So we can wrap our D2 branes around these 2 compact directions. We know what are the supersymmetry constraints on these states, and we can include them in our calculation. And indeed, their contribution seems to be precisely the finite constant term that we need for this amplitude, as well as a series of worldsheet instanton corrections which were completely absent from the Greenwood-Perle-Van Hove calculation, but they knew they had to be there, so they just had to add them by hand. And in fact, if you combine this also with the Kaluza-Klein sector of the theory, which is still present, you will obtain the complete result in AD by one self-consistent calculation, including also the logarithmic terms that perhaps the more experts in the audience will recognize as necessary to impose modular invariance of this result. And in fact, similarly, also in 7 dimensions, the same story goes through. We can get a complete result, obtaining also terms that would otherwise have to be added by hand in the original formulation. But of course, the natural question is, how much further can we check this? And the problem is also, in a sense, very practical. The lower in dimensions you go, the more particle states arise, and then solving the supersymmetry conditions becomes more and more involved. Despite these technical difficulties, we were able to perform a series of non-trivial tests for this amplitude. First of all, verifying that the pattern of the previously ambiguous constant term arising from contributions of extended objects persists not only in 7 dimensions, but also in 6 dimensions. And in fact, it is always apparent if you actually perform the same calculation now in the perturbative string theory limit, where our technique is still applicable. Additionally, one can perform a complete instanton analysis and verify that we get all of the various instantons that we would expect to find contributing to this amplitude in various dimensions. Observe that we are also getting the Euclidean D4 instanton brane contributions, despite the fact that D4 branes were not part of the light spectrum of the theory. And what I find to be even more intriguing is that it seems that the emergence proposal, or rather its M-theoretic refinement, seems to work for us as a physical principle compatible with the mathematical properties of these amplitudes. Now, these R to the 4 term, as well as some other similar amplitudes, were conjectured to be given by a particular modular form called the real Eisenstein series. And what I have been telling you is that we were performing a calculation on the strong coupling M-theory limit for this coupling, and we were able to obtain the complete results valid across our moduli space, also in the perturbative string theory limit, and anywhere else in the bulk. And mathematically speaking, this would not be possible if it was not a degeneration limit of this modular form. So this already brings me to my conclusions. What I was presenting to you today was a concrete test of the M-theoretic emergence proposal, where what we did was we extended the ansatz of Greenwood, Perle, and Van Hove to include the entire spectrum of light states present in our theory, rather than just focusing on the Kaluza-Klein subsector. So I repeat here, I'm including also wrapped M2 branes as well as wrapped M5 branes, which I should also mention usually have a less clearly understood role in the context of M-theory. And it was very crucial in carrying out these calculations that we could also identify an appropriate regularization scheme, which was just a very simple algorithmic process of 3 steps, which was crucially depending on going beyond our usual field theoretic intuition about summing only contributions up to some particular energy scale, but actually summing over the entire infinite spectrum of states. So in a sense for us, the species scale was just working like a filter, telling us which towers are relevant for our calculation, but then we really needed to integrate out the entire towers appearing. And the upshot of this approach was that we could self-consistently obtain the complete results in dimensions 8 and 7, where so far this physical approach could not be complete. And in fact, we were even able to make precise instanton predictions for any dimension up to and including dimensions 4. Additionally, we were even to gain a physical interpretation for terms that were previously ambiguous, either because they were formally infinite or because they were completely absent. And we were able to basically connect some pre-existing, more mathematical arguments to our physically motivated swampland approach. And I would like to close with some obvious future directions that actually we're also pursuing at the moment. Well, first of all, it is possible that this idea of emergence can give us non-trivial hints about the microscopic structure of string theory amplitudes that perhaps we are already very familiar with, but we would not be expecting them to have such degeneration limits, such as the ones that are already known for terms like r to the 4. So it seems that there's also a possibility that we have non-trivial cancellations among the various terms, which were so far, at least to the best of my knowledge, not known. Additionally, we would of course like to extend our understanding in our calculations beyond the easier setup of one half PPS saturated quantities. And of course, a more long-term goal would be to actually extract some information about M theory itself, whether that is linked to some particular formulation of it, such as a matrix model or any other alternative approach. So with this, let me stop here. Thank you very much for your attention. I'll be happy to discuss your questions.
Thanks, Antonia, for the nice talk. Are there any questions? Yes, George.
Yeah, thanks. That was a very interesting talk. Could we maybe go to the second slide? So again, it might be a basic or naive question, but to understand here, yes, the whole swampland program where also your proposal and its testing comes in. So what is the goal here? Is it to constrain low energy effective theories that have a quantum gravity description? Is that the main goal?
Yes, precisely, because the thing is that so far, I mean, effective field theories have very rich tool work, but it seems that there's also EFTs which we believed were consistent, but actually, if you try to extract information from the UV, they are not really consistent.
But then there is an elephant because there is also the landscape. So that I imagine means that it's also a very huge space for low energy effective theories. And so how predictive is this really?
It is a very large space, but first let me point out that these very exciting numbers that you might have seen in the literature, like 10 to the, I don't even remember, are actually already too much. We are in much smaller numbers if we actually take into account swampland considerations. We know that it is a finite landscape. Indeed, at the moment, I cannot tell you that I have two theories, let's say, but it seems that definitely there was some overestimation of how big the landscape could be, as swampland tells us, at least.
Maybe if you could follow up with like what you just said. Do you know it's a finite?
Yes, I think it has been.
What's the argument?
Yes, unfortunately, I'm not an expert on this, but I think there are some finiteness argument. And in any case, even these numbers that I referred to as crazy, not crazy, but as overestimations were already finite numbers. It was not some parametrically. Yes. Yes, yes.
You mentioned at the last transparency some work or hope to extend this to not 1/2.
Mm-hmm.
Did you mean 1/4 or so, or even non-supersymmetric?
Well, actually, that's a very good question. At least for some amplitudes, like r to the 4 and derivatives thereof, there have already been conjectures, even for the cases of these amplitudes not being supersymmetry protected, so much higher order of derivatives, that they are given by mathematical expressions which are very similar to what we had here for r to the 4, which again would have the same degeneration limits, or to put it differently, would again exhibit the same pattern, that you only need a subset of the entire particle spectrum to obtain the full amplitude. So there is hope, at least even for this very restricted set of couplings, that also there our results can directly extend. Yes, yes, some of these coupling, after I think, after a certain order of derivative of r to the 4, there's no longer supersymmetry there are no longer supersymmetry constraints, so you could in principle have any perturbative contribution, but there have been people studying these objects claiming that no, still they're given by an amplitude of this type, which if you make a perturbative expansion thereof, only has finite perturbative contributions.
Yeah, I didn't understand the new regularization.
We're coming for you.
Can you explain a little bit more this new regularization description?
Sure. So what we're doing, for example, in this simple setup in 10 dimensions, I have only one compact direction. I only have D0 branes, Kaluza-Klein modes there to integrate out. So this leads me to this expression, where here I'm first performing the integral by introducing some UV regulator epsilon. Then the integration is possible. I can perform it. I am minimally subtracting all the orange terms here, which just encode information only of this regulator, but then still I have an infinite set of summations to perform. Here only one, but in principle I would have many more summations to perform, which I'm performing as a final step.
How do you do the subtraction? Usually you would need, after the fourth term, subtraction. Are you putting a counter term?
No, this is just a minimal subtraction. I'm throwing them away, effectively.
Why is this justified?
Well, first, yes, so just to be more concrete, this can generally be done in the cases where we know that these amplitudes can be compatible with having an analytic continuation, so, which has been proved already more formally for all of this amplitude, for this amplitude in any dimension, with dimension equal to 8 being slightly more special, in which case indeed we had to subtract only a part of the regulator, which would allow us to restore modular invariance. But in any dimension where you know that this amplitude can be analytically continued without any problem, this method is justified because you know you have a finite thing to begin with.
The results, including all particles up to 7 dimensions, are known since the 90s. The problem was at the time that in 6 lower dimensions, particularly 6 dimensions, there were contributions that were not understood. Is there any progress in that?
Yeah, so first of all, I think you're referring to these instantonic 1/GS² terms that were there. I think, first of all, I think this has already been discussed in a much more recent paper by Paolin, where he, if I'm not wrong, I can look up the reference for you later, where he is claiming, and actually this is also what I believe, that these terms were actually appearing because I think it was not completely clear what would be an appropriate regularization scheme of these amplitudes. As you know, for this particular modular form, there's various possible representations that people can consider, and I think in some cases the instanton terms that you have in mind are actually related to precisely taking some representation and applying some regularization, not being compatible with this representation. But in any case, as I promised, we have actually explicitly checked that we can get all of the correct instanton contributions and no additional ones. So you can actually do this exhaustive, write down any possible bound state you can think of, and see what type of terms come up. Actually determining their precise numerical prefactor is what is very tedious in these cases, because you need to properly sum over all of the bound states, but no additional instantonic contributions arise.
Okay, so let's take Antonia again, like for the nice presentation. So we're running a little bit late, so we're going to take a break now, coffee break, and we can resume like in 15 minutes to 11. άμα το έχουν από εδώ. Αυτό πρέπει να δουλεύει μπρος πίσω.
Ναι.
Okay. Έχω και ο pointer.
Τέλεια.
Εντάξει, okay. Λοιπόν, ο Βασίλης θα κάνει το share.
Ναι, χάρηκα.
Let's start. So, let's start with Πρωί Χριστίνας Tarasi, but speak about journey through the non-geometric landscape and connection to the softland. So, please, go ahead.
Okay. Thank you so much. Thank you for having me here. I'm very excited to talk at home, I guess. Okay, so I will try to give you an overview about how things came to be and how I kind of think about things, more generally about recent work, and how my work in the landscape also connects to questions in the swampland. And it will be based on this kind of papers, but I will try, there will be some more technical slides for more experts, but I will try to give more of an overview. Let me start by saying that our general motivation is quantum gravity, trying to understand quantum gravity and different aspects of it. We all know quantum gravity is hard for various reasons, whether it's our usual framework doesn't work as well, whether that we don't know what's the right questions, and what kind of quantities could be predictive. And it's very hard when you don't have much experimental evidence to work with. So I would say some important questions would be, okay, so what's the right framework of quantum gravity? String theory is a candidate, and if it is the right answer, then how do you show that this is the right answer? How do you make quantum gravity or string theory self-predictive? And where are we within the string theory landscape? Okay, so this kind of seems to suggest, I would say, kind of a hybrid bottom-up, top-down approach where you're both trying to understand deeper aspects of string theory together with deeper aspects about what is quantum gravity and how it relates to things that we have constructed. But before I start, we already had an introduction on the swampland, but maybe I should just say a couple of things again, that at the end of the day, we know how to write effective field theories. So you write down your favorite effective field theory, and you ask, when does this have a well-defined UV completion when coupled to gravity? So for various reasons, we don't expect that the whole set of effective field theories are UV completed. Even in quantum field theory, you wouldn't expect that all EFTs you can write would be UV completed. So in gravity as well, you wouldn't. But there is a big distinction which I will come to. But before I come to that, I would say that we have words for this, and the EFTs that are not good with gravity, we call them in the swampland, and the ones that are good, we say they're in the landscape. So a big, or at least a subset of the landscape is definitely the stringy landscape. Things that we can actually construct in string theory, and they have a UV completion within the string theory framework. Okay, so this swampland program, in a way, can be thought as two different things. Trying to understand either the boundaries, in a way, between the stringy landscape and the actual landscape, like how much of the string theory of the actual landscape is within the string theory landscape, and also how much of what we would call a good quantum gravity, how do you define it, and what are the boundaries of this? So the study of string theory definitely would help us understand more this, and maybe gives us insight on the other boundaries. Okay, so there is good motivation that there is a finite number of UV completed theories in the landscape, and this came up as a question earlier. I would say that the motivation comes a lot from string theory. There are motivations and kind of bottom-up arguments using black holes. I wouldn't say that necessarily there is very concrete evidence, other than the fact that in string theory, definitely with enough supersymmetry, you do expect to have a finite landscape. So, but I think that an important question, if you want to understand at least this distinction, is to say that, okay, if it is a finite landscape, let's say within string theory, well, the actual landscape better be finite, at least, and then start the matching. And if that's true, if your actual landscape is finite, then string theory does look kind of universal. So let me give you an example. I will not go into too much detail, but it also relates to the question asked earlier. And I would say that if you have string theories with 16 supercharges, so you have enough supersymmetry, we already know constructions. So in 10-dimensional, because of chiral anomalies, you just have you have more options, which I'll come to, but the two that are consistent string theories are here. Then in 9D, you just have, this is the rank of the gauge group. You have constructions with only those ranks. And in fact, there is global gravitational anomalies, why you cannot have other ranks. Similarly in 8D. In 7D, also there is specific ranks that are possible for different gauge groups. And in 6D, there's also an evenness, and we have less of a clear understanding exactly what theories arise, but there are, I mean, I couldn't put all references. There are many constructions. We also have some constructions, which I will talk a little bit about later. But there is definitely a pattern on what kind of ranks. When I mean rank, I mean like take your favorite super young males with 16 supercharges coupled to gravity, and which ones are consistent together with gravity. So this is what comes from string theory, and one thing that is also universal, except the patterns that you see in the rank, is also that the fact that the rank of any gauge group is bounded by 26 minus d. Okay, so this is from top down, and in fact, in 19 with Kamran and Hicho, we argued using swampland principles that it better be that the rank is actually bounded by 26 minus d independently of the UV completion. So at least, I mean, I will not describe the details of this, but I will say, firstly, it's very non-trivial in a sense that I could have written an effective field theory of arbitrary high rank, and in principle, coupled to gravity, there shouldn't have been a problem. The second thing that was very important is the fact that you have enough supersymmetry such that your moduli space does not get corrections, and it's easier to understand infinite distance limits that actually provide this bound. So later, much more work, which again, I'm not trying to be exhaustive, and earlier work has shown that, for example, this is an earlier work that you could have had more gauge groups in 10D, but there's issues with this. The fact that the ranks have this pattern seems to have to be related to different types of anomalies. in another work that we studied the entire moduli space for theories in 9D. So there seems to be a pretty good match. Whether we're talking about the rank of the gauge group being bounded and the bound being the same, but also what kind of possible theories can arise and how much they match with string theory. So this is towards string universality. So at least for supersymmetric theories, we have a good understanding on how much the actual landscape with the string landscape overlap, and it's pretty much overlapping. So as you go down in supercharges, I would say questions become much harder. I've worked, there's been also more recent work in finiteness questions, which I'm not really talking about, but I just wanted to give you an idea about what's the interplay between the string theory landscape and the swampland. But one thing that you probably noticed is that how would I have known about 26 minus d if it wasn't from string theory, right? I wouldn't have guessed it by myself, but rather string theory gave me a guess, which then I tried to argue without using string theory. But that means that a lot of my intuition does come from string theory itself. So that means I better have a pretty good understanding of the landscape if at least I'm trying to make a proposal. Okay, so the point here is that we do have to be careful because a lot of your intuition in string theory comes from compactification. Okay, and when you talk about lower supercharges, lower dimension comes from compactification. The most well understood compactifications are geometric, like Calabi-Yau manifolds, etc., or brane constructions, things that you can construct and see. And sometimes we can end up thinking that this is all that is. Two examples, I would say, for those familiar, is that in 6D, six-dimensional theories with 8 supercharges usually come from F-theory compactifications on elliptic threefolds. These are the biggest classes of theories we know. They have to satisfy something called the Corrara condition for elliptic threefolds. If you're not familiar, it's just basically an inequality that can be thought as relating the tension of gravitational instantons and tension of gauge instantons in some particular way, which is highly non-obvious. You could have said, and I have tried to argue it from bottom up. I couldn't. It turns out there's a good reason why I couldn't, which also gives you a little confidence on the swampland principles that I couldn't actually do that. And the second thing is that geometric models always come with a neutral scalar, a scalar which is a modulus that actually controls the volume of the geometry. So this also is in general very typical, but it doesn't actually have to be the case when you study non-geometric models, which we will discuss later. So I think the point here is that going beyond geometric and nice models that we understand well can give us a better understanding of more exotic and different corners of the landscape and understand this boundary that I was talking about earlier. Okay, so the lesson that I would say here is that the swampland program string theory has a give and take relationship where you learn, where you hypothesize things that could potentially be true that you see typical within string theory and then try to argue them from bottom up. But also when things fail, when you cannot do that, you go back and ask, is there maybe a construction? Is it that I didn't understand the string landscape well enough? And that motivates you to look for counterexamples and new kinds of constructions. Okay, so now this brings me to the landscape, in which case you can say, what do I want from the string landscape? Okay, so what do I want to understand? So from the supersymmetric landscape, I guess one thing we always want to understand is the most wonderful thing that string theory has given us, which is dualities. The idea that you can understand when your effective description breaks down, there's another description that becomes important and explains your new degrees of freedom, describes your new degrees of freedom. This is a very powerful tool. So, but when you, even with low supersymmetry, it's still not obvious how to find certain dualities. Then you can ask about what's the right swampland principle. Since we have more control, we better be able to, at least in supersymmetric theories, have the right ingredients, similar to what we were talking about earlier. And then whether string theory is universal. If string theory, if somebody was to tell me that, you know what, string theory is universal in any supersymmetric theory, I think that I would be much more inclined to believe that this is the case in general. Because even though supersymmetry is helpful and gives me more control over my effective field theories, it's still not enough, even with 16 supercharges, to show me finiteness. And from non-supersymmetric landscape, I mean, there are obvious things like standard model physics, cosmological physics, naturalness kind of questions that we want to understand. And some of these are connected to understanding these kind of things in non-super-Z context. Like, can I understand what duality really means in the non-SUSY context? Could it help me understand different aspects of potentials? What are the swampland principles outside of the supersymmetry? What do I even mean by moduli space when I'm talking about theories that don't have supersymmetry? And again, similar to the question was asked earlier, finiteness kind of questions and string universality. Okay, so what do we kind of want? I would say is that we want some generic features, as I said, what is typical. You always want to know exotic corners so that you don't get blinded when you talk about what is typical. And you want semi-realistic models and, of course, modular stabilization. So I will talk a bit about exotic corners and how they relate to the rest. Okay, exotic corners need exotic models. So one type of, I would say, more exotic would be asymmetric orbifolds, which are non-geometric. By non-geometric, I mean that you don't have a nice way of writing down a supergravity and doing a compactification. But before I get to this, just an orbifold crash course for maybe that people that are not as familiar. Consider just a simple compactification of your favorite effective field theory in a circle. This is a KK compactification. Then there exists a Z2 symmetry on the circle where you can identify, for example, antipodal points. This is called an orbifold. So when I quotient the S1 mod Z2, this is what I would call an orbifold. And geometrically, it would look like something like an interval. Now, of course, this is a singular geometry as a geometry because what happens at the endpoints. But string theory, in a way, resolves this by stringy effects. So string theory tells you that actually there is things living there. And modular invariance of the string worldsheet specifies your consistency and the type of degrees of freedom you get that kind of resolve those singularities. Another way to think about this is that the string theory charge lattice is a gamma 1,1 even unimodular lattice. Why? I have KK mode, I have winding modes. The different charges form a lattice. The lattice has a symmetry, which I'm orbifolding, and then string theory modular invariance will tell me exactly what kind of spectrum I get. And there's two things. So there's the untwisted sector, which is this sector that an effective field theorist would get if I tell him, you know what, go and please find the spectrum that is invariant under my action. That's the obvious thing. And then there's the twisted sector, which is the, because string theory is a theory of extended objects, you can think of it as having, for example, strings that are closed up to some action. And these are the more stringy effects in a way that complete the modular invariance of the string theory. Okay, so now to dive into these orbifold examples a little bit more, I should say that how do we start? You choose your favorite starting point, you take your type 2 or heterotic string theory, some nice perturbative description. You choose your even modular lattice. Usually we do that. This is a gamma d, d, or with a gamma 16, 0 if it's heterotic theories, for example. You can pick a lattice related to assembly algebra. This is basically describing your torus compactification. Then you want to study lattice automorphisms. These are crystallographic symmetries of the torus. For example, the Z2 was the example I studied earlier. And then you can choose a twist and a shift along those directions, and they act on the Hilbert space in this form. So this is the twist, and this is the shift, where P left and P right are in the lattice. And we then distinguish two types of orbifolds: the symmetric, where the left and right sectors are the same. So this is what I would also probably call geometric. And then there's the asymmetric orbifolds that are left and right asymmetric. It's not also as exotic, asymmetric orbifolds by themselves. You could think of it as T-duality itself is kind of like an asymmetric action, where if you think of it as an action, it acts differently on the right and left movers. Okay, so let me give an example of a model. As I said earlier, we had counterexamples in certain things. So we have a heterotic asymmetric orbifold where we picked our favorite lattice. We picked an action. So this is a Z3 action with a shift on a heterotic orbifold. And we ended up with a matter that looked of this form, E6, SU3, E8, and SU3 squared, and charged matter. So this theory, why is it interesting, is because it has no neutral hypers. It means that it doesn't have any neutral scalars. Doesn't have any neutral scalars means that it's definitely not geometric. So I was telling you earlier that in every geometric construction, you at least have one neutral hyper, which means that this model, in a way, could exist at a place where the volume is frozen. So definitely, we shouldn't be in the geometric lamppost, and we are somewhere out here finding kind of different types of examples. The other thing is that this theory, so we didn't know a counterexample of this, so any 6D theory with 8 supercharges, which is exactly what this compactification gives you, from the elliptic threefold point of view, was satisfying the inequality I told you earlier. It turns out that in these orbifolds, this inequality is no longer satisfied. So this is a counterexample of this general inequality, which kind of looked like universal. It was at least universal within the geometric landscape. Let me also connect it a little bit more so it doesn't sound too bizarre. So we do believe, when we believe that things are finite, we also believe they're connected. So how are things connected? So in this case, I gave you some very non-geometric model with some weird charged matter, some gauge group. It has also one tensor multiplet and no neutral hypermultiplets. But if you Higgs this, if you Higgs the gauge group here, then you end up in a theory that has a gauge symmetry E8, no charged hypers, and everything is neutral. So this, to some people that are experts in this, could be familiar, and it's actually an F-theory based compactification. So in fact, this, through a Higgsing, is related to an F-theory compactification and a heterotic theory. So in fact, we are at a point where the size of that compactification is frozen, so that you're actually tuning also that extra multiplet to arrive at this asymmetric orbifold. And this is telling you that there's a duality chain where you can actually understand this asymmetric orbifold that we constructed from the heterotic point of view that has a perturbative description, giving you a nice picture of where are you from the F-theory point of view, and you are at a point where the base has shrunk to stringy size such that the supergravity approximation is broken down. There are also models in 5D with no hypers. These were models that we did with freely acting orbifolds, but I should go a bit faster. Okay, so I can tell you that there are also more exotic models. So we also have what we call the quasi-crystalline orbifolds. Quasi-crystalline orbifolds are the following. So So I talked to you about you picking your favorite lattice and then picking a symmetry of the torus and quotiening by this. However, in string theory, what's the fundamental thing is really the string lattice, not as much your torus. So you could have picked a symmetry that is not necessarily a symmetry of your torus, of the geometry, but it is a symmetry of the string theory. So quasi-crystalline symmetries are basically that. They act crystallographically on the gamma d, d torus, but not on the d-dimensional torus. So by default, the quasi-crystallographic symmetries are not left and right separate automorphisms. As I said, they're not automorphism of the torus. And by definition, they're going to be asymmetric. So this gives you a bigger class of theories that you can do. In fact, these symmetries leave at points where your Narane moduli are fixed. You also have to turn a B field, a background B field, and everything is rigid and fixed, which means if you're looking for theories without many neutral scalars, these are pretty good compactifications. This is just a diagram of how this kind of look like. This is the lattice, in which case, if you think about the orientation and the center of the ellipsis being left and right, you actually have to rotate both to have it as a symmetry. So it doesn't have translation symmetry. Okay, so we have some theories with 16 supercharges. Of course, somebody with 16 supercharges in 60 knows that it's just the K3 sigma model, really. So these symmetries better be part of the K3 sigma model. And in fact, they are, because the rank is 20. And it turns out that in this work, they have predicted different orbifolds. So for example, you know that K3 has a T4 mod Z2, Z6, mod Z3 orbifold points. But in fact, it also has Z5, Z8, Z10, and Z12, which are quasi-crystalline orbifold points. Another interesting fact about this is that you can get pretty large discrete gauge groups, which is usually not easy to construct. So you can get something like a Z42. Then you can consider doing a free action on top of this quasicrystal, and you end up with theories in 5D that look as they come from 60 islands. What is an island? An island is a theory that has only the gravity multiplet and has only one scalar consistent with only one scalar in the gravity multiplet. Now, why this is interesting, it's pretty rigid and isolated. So we already knew one example of a string island. So if these do have 60 decompactifications, then they're new. And in fact, in this work, it was predicted that in 60, there should be more string islands that we don't know. And in a work that should appear, hopefully, at the end, like this month, before the year ends, we have constructed all these new string islands and completing the classification of theories with 16 supercharges. We have also theories with discrete theta angles, which correspond to RR axions, where you have a fractional charge that shifts the lattice, and you have charges occupied by non-BPS particles. This provides a counterexample to your BPS completeness. It's a proposal about having a spectrum by having, when you have a lattice with enough supersymmetry, then they should be occupied by BPS states. Here, obviously, there are states that are not BPS. And also the lattice with gravity conjecture. So another interesting point about this is that you can actually try to understand their S-dual. And in fact, they're S-dual to the quasicrystals I just described earlier. So there is a Sen-Vafa prescription where you can understand U-dualities and see that in fact the islands that we have constructed have only one scalar, so they only have a strong coupling, and the strong coupling turns out to be these quasicrystals. Okay, so I can tell you, maybe I don't have much time, but I can tell you a little bit about also applications to non-supersymmetric strings. It would be interesting to have string islands which are non-supersymmetric, meaning that you just have one scalar to just stabilize, right? That's it. At the end of the day, that's what we kind of want, to not have a lot of instabilities. Usually, it's not very easy to do. I can tell you a few examples where at least a leading order, you have no tachyons, and you have only one neutral scalar. So this will be examples similar to the heterotic O16-O16 string. And they have positive leading cosmological constant, chiral matter, no tachyons, and one neutral scalar. So there's a quasicrystallographic orbifold in 4D that gives you this. You have a big gauge group and charged matter. The theory has no tachyons, as said, at tree level. And it's not a special point, so there's no rank increase. Okay, and one neutral scalar. We also have similar examples in other dimensions, like in 6D. So there's another asymmetric orbifold in 6D, where you have, again, no neutral scalars and no tachyons at leading order. And one more, this has even less matter in 8D. Okay, so basically, we have some nice examples of theories which are not supersymmetric, have no tachyons at tree level, They have chiral matter, they have standard model-like kind of gauge group and charged matter, positive leading order CC, and one neutral scalar. It would be really nice, and this is something we're actually working on, to have models that actually have only one neutral scalar and no charged scalars. Okay, so let me just finish up and say that I think in general we are working, and I think it's very interesting to understand better all corners of the string theory landscape, because it influences not only our understanding of the landscape but also of the swampland program. A lot of these ideas, I talked to you a little bit about S-duality and dualities, and how this theory with one modulus, we could understand its S-duo, which is not easy to do in general. It would be really nice to be able to have results like this in the non-supersymmetric context, where you could potentially understand the fate of theories at different corners. And then a better understanding of other exotic models, for example, non-perturbative convectifications, possible, would be really nice to be able to do. There's still U-dualities you could caution by that you don't necessarily know the consistency. And I think one remark that I would like to point out again is that for me, the string theory, the understanding of string theory and the swampland are very related. One feeds into the other. One is guiding the other. And I think if we want to understand quantum gravity, both the bottom-up and top-down approach are very important to understand these details. Okay, thank you very much. One second. Thank you. I want to advertise also that with Cameron and Alec Vitroya, we are organizing a conference, Lotus on Swamplaria, in Naxos, my favorite island. And we encourage people, especially young, both students and postdocs, to apply and join us if you're working in things related to swampland and landscape.
Thank you. Thank you. Questions? Kostas?
I have two. One is a general question. So you were discussing about the string landscape or swampland. Should we distinguish between perturbative string theory landscape perhaps?
For me, I would say that when I say string theory, I mean perturbative, a lot of it. I think when you talk about non-perturbative or strong coupling, you might not even have strings. Or you might not have a worldsheet description, or you won't have a worldsheet description the way we understand it. I think that you could have indirect ways to understand things like F-theory, something like that, that might not have any perturbative limit. So I don't know, like the distinction between these two, for me, is not as relevant in the sense that we call the whole thing string theory, and then depending on what aspect we're studying, then you focus on that. So if I'm talking about worldsheet physics, then I'm obviously talking about perturbative string theories. Also, like if you want me to do an orbifold and that is non-perturbative, in certain cases you can understand that, like a Hojava-Witten wall, maybe F-theory. There are cases that in principle you can try to understand, but if I don't have something like modular invariance to guide me, it's not obvious, or anomalies or something like that, it's not obvious that this is consistent. I think that in principle, it depends on what you want to add. I think you can do I think you can think about it more like quantum field theory, where you can understand things order by order. And I mean, calculations are hard. But in principle, if I could do loop calculations, I could understand higher loops and understand much more details and much more defined structure. So I don't think this is necessarily where it's as important, which it is because it's hard, but I mean like it's more like on a technical aspect. I think if you tell me though, like maybe we don't leave at a perturbative corner. Maybe like where we are is not a perturbative corner. Maybe we're somewhere else in the middle of the moduli space. Then how would you know? How would you construct that? Then in that case, you would also need a non-perturbative approach, but it's not easy. And I do agree that it's needed.
From what I remember, in advanced matter, when people talk about quasi-crystalline structures, typically they
it is what it is. Yeah. Yeah. Why? Because the torus, right, is d-dimensional. The string lattice is gamma d comma d. So the symmetry acts crystallographically on 2D. So it acts crystallographically on the torus, and that's why, like this lattice picture I had, you had to turn p right and p left. And that's why it's not the symmetry of the torus. You have to turn on B field. And it's a symmetry of the string theory. Okay, no, that's a good question. So I think that what I call it depends on what we call swampland conjectures. So usually swampland conjectures, the ones that we trust, are very open-ended, very general, okay, and usually not useful.
All of them.
I'm saying like usually they're all very like they don't give you a lot of details. Usually you need to refine them. Yeah. Okay, so you're pushing. So it makes sense, right? You're pushing to refine until you see that there's a counterexample and then start going back, right? So you're trying to make it more and more strict, and then you see that, oh, okay, this is actually wrong, and then you can go back. So for example, we know that the lattice with gravity conjecture is not true, but the sublattice doesn't have any counterexample, so that there's a sublattice that satisfies it. Similarly, for the BPS completeness, it's a pretty strong version of. So let me give you an example. In that case, what is the conjecture is completeness of spectrum, which is related to having no global symmetries in a theory of quantum gravity, which we pretty much believe in general. It has arguments from holography, it is CFT, black hole physics, there's a lot of arguments. Now, if you want to say that also, if a state can be occupied by a BPS state, it's an extra step. You see, it's an extra step. And then you can say, like, do I know a counterexample? So up to now, we didn't know a counterexample. So now you know a counterexample, but you still have a whole sublattice. So it's about refinement. So, does this answer your question?
I think it probably shows that the swampland program, well, you mentioned in your early slides, without any experimental data on the quantum nature of gravity, it's very hard to just be guided by theoretical principles.
Sorry, in theoretical physics, we've been guided by theoretical principles for quite some time. We've built billion-dollar experiments because of theoretical predictions.
No, I agree, but
so I'm not understanding the point.
Well, you say you specialize certain conjectures and then you find counterexamples and you have.
No, I think that's not a fair. I think that that's not a fair point of view. I think that making a general conjecture about completeness of spectrum and no global symmetries, which is pretty well understood and pretty well believed from very different approaches, is one thing. But then understanding the boundaries of this, like how much do you constrain it in theories that have enough symmetry, like supersymmetry, and then trying to understand where this ends, I think it's a different thing. So I don't think this is a fair description of it. No, I'm not arguing. I'm just saying that it's not.
I'll take one more question, right? So, George.
A very general question. From the point of the effective field.
Yeah.
What I should consider the main feature of your models? Something like new symmetries, new spectrum, new superpotential. What you would expect in the spectrum?
Sorry, I didn't understand the question.
From the point of the effective field theory, what one should expect from this kind of non-geometric approach?
Okay, so all this all string theory compactifications are things in. Okay, I wouldn't say all, but at least all non-geometric compactifications are not things you would see in effective field theory. Part of the reason is that, I mean, even in geometric, okay, again, even if you're doing S1 mod Z2, if you were just putting a theory in an interval, in principle, you might not even know about twisted sectors unless you have some anomalies. You can understand the kind of like boundaries, domain models, and things like that you might have. String theory gives you more objects. String theory has extended objects. So it will give you more states in the theory. There's going to be things that wrap things. There are going to be things that are identified up to those symmetries. So the spectrum is more big. You can think of it more from effective field theory point of view, that when you have a singular geometry, string theory gives you a way to resolve it back to something geometric. Not geometric, back to something smooth, but in a different way than geometry would. This is how you can think about it from the effective field theory point of view.
Thank you. So, hi everyone. Let me start, of course, by thanking the organizers for inviting me in this nice initiative. Let me call it like beyond the standard XMAS workshop initiative to present my work. And okay, even though our motivation for this work that I'm going to present to you today is started from theoretical base, at the end we realized that it has a very nice phenomenological implication. So now let me shift the discussion from the previous talks to something which essentially works on the interplay between theory and phenomenology. So in principle, I'm going to show you how some simple extension of the gravity part of our standard gravitational theory essentially can provide us with a very nice candidate for the dark matter, plus the PTA, which is pulsar time array measurements, but I will be more explicit about this later on. So I will try to show you how this simple extension can be really informative and give us some candidate which actually can also constrain the searches and pin down the searches about dark matter. So this work is based essentially in this published paper here in collaboration with Eugenio Mejias, with Stefan Pokorski, and with Mariano Quiros. So I will start with a simple motivation and simple introduction to give you, so everybody can be thermalized with my work. And then I will give you the information about the dark matter candidate, or the dark sector, if you like, in general, candidate or setup that we are going to use. And then after I will explain all this theoretical situation, I will show you how our dark sector, dark matter, our framework can compile and how it does behave under the constraints of the correct relic density and abundance of the dark matter, and how it behaves under the constraints of observational signals. And then I will conclude. So, okay, I do not have to convince nobody that dark matter exists. We have a lot of information in different various scales, like galactic scales, like cosmological scales, cluster of galaxy scales, that they give us information about the existence of something which is dark, non-baryonic, and it has some very specific way of interacting. So after all these observational signals, we can conclude that essentially 84%, almost 84% of the matter in the universe is dark, and we don't know what is it. We know that it exists, we don't know what is it, so what we need is a candidate. And in principle, we have some information about this candidate, that it should be stable, like corresponding to the lifetime of the universe. It should be essentially dominantly non-relativistic, should be cold, according also to the lambda CDM models that we have. Should be electrically neutral, colorless, and essentially we know, that we are sure about this, that it interacts almost or only via gravitational interaction. However, this gives a kind of standard problem in these situations because you see candidates like this, dark matter candidates like what I described previously. For example, I give you a very broad example, which is the WIMP miracle, as it's called. It inherits some conflicts between the processes that gives you the relic abundance, the correct relic abundance, and it has some conflicts with the indirect and direct and accelerator searches, just because all of these processes include the interaction of dark matter with the standard model. So there are some standard problems in this direction. And on top of that, what we know already is that there is a kind of dark matter zoology. There is, imagine this, that is a center brand. This is dark matter. You want to understand what is dark matter. And then there are several sub-branches which could, in principle, explain the origin of dark matter and give us a candidate for the dark matter. So the point is that you can see that there are several directions, like from macroscopic candidates, like primordial black holes, to some ultralight particles like the QCD action or action-like particles, extension of the candidates coming from the weak scale, and extension of the gravitational part of the standard description of particles and gravity that we have. And in principle, all these directions give you a candidate, but on top of that, they give you a mass range. So another problem of this discussion is that there is 80 orders of magnitude in the mass range if someone takes into account all these candidates. So essentially, experimental searches are not so well pinned down because there is a vast difference in the orders of magnitude according to what you're talking about as a candidate, like ultralight dark matter, 10 to minus 22 eV, electron volts, or to be like a primordial black hole, which is several solar masses. And in principle, I can say that maybe there is another branch still missing, that it can give the final answer about what dark matter is at the end, but I think that it is already too much. So for this talk, I will concentrate on the extra-dimensional part. And specifically, essentially, I will do a simple extension of a standard framework, extra-dimensional framework, which is the Randall-Sundrum model. And I will give some brief also introduction about this. So what we see is that if you do this extension, which is essentially taking the standard Randall-Sundrum model and extending it with an extra brane, the dark brane that I said in introduction, I can show you that there would be a nice dark matter candidate with very nice features, among other things, and it will narrow down a lot the searches, the experimental searches for the mass parameters. So let me start with explaining to you the dark matter setup that we have. So the standard Randall-Sundrum model, actually this is the standard picture of a Randall-Sundrum model. This is the metric, let me call it low temperature or zero temperature if you like metric, the confined phase of this model. And usually there are two branes in this model and a wrapped fifth dimension. It's a 5-dimensional model. So there is the Planck brane, usually empty, which has a scale, which is the Planck scale. And all the scales in our case will be denoted by rho tilde, rho 0 tilde the Planck brane, rho tilde t, the TV or standard model brane, where also in our case the standard model lives there, is confined there. And then we have the dark brane, rho tilde 1, where we have, first of all, the extension of a new brane, dark brane, and a candidate, dark matter candidate, which for us now it could be a fermion, chi. It could be any dark sector, but for us, for this discussion, this is enough. So in the standard picture, you have the graviton and the radion, which are excitation of the metric propagating in the bulk. And plus, in order to stabilize these branes here, you have also an extra field which comes from the Goldberger-Weiss mechanism, this phi, which also lives in the bulk. Now, phi and the dimension, the extra dimension here, both they are reparametrized to give you the radion, actually, what I said here, the final version of the radion. But for our discussion here, Just keep in mind that this brane is introduced in the TV scale just to solve hierarchy problem. This was the initial motivation anyway of introducing such a model. And in our case, we keep this and we add this brane. But mostly, I will talk about this discussion here, this part here, which has a light radion, and here is a heavy radion, so we can forget about this. Plus, that the graviton interactions, I will show you later, but I'm telling you already, that are very, very weak. So essentially, whatever I will show you here has to do with the interaction via radion. And that's all. So in principle, this setup here, with standard model here, and a dark brane with this particle here, I call it kind of Occam's razor, and there is a reason about this, because okay, one interpretation of Occam's razor is that it can solve. You try to solve the biggest possible problems in the smallest possible, in the easiest possible way. Let me put it that way. So here, what we can solve. First of all, this solves one theoretical problem of the standard model, which is the Higgs hierarchy problem. On top of that, it gives you, and I will show you that this is correct, a very nice candidate for a dark matter particle. And on top of that, to connect it also with some recent observational signals, maybe you have heard and know about this, that almost 1 year ago, there was announcement of the PTA collaborations that it was measured stochastic gravitational wave background in a very specific frequency, nanohertz. And this model can also provide an explanation about this, given that this signal comes from some cosmological origin and not from some supermassive black hole, astrophysical origin. But let's assume this. So in total, you have a framework like this, which can solve many things or explain many things at once. So in that sense, it's Occam's razor. But let me explain why the PTA. Because you see, okay, this is an extra dimensional model, and as I said, this is the standard Anderson model, which has this metric if the temperature is low or 0. But if you go to higher temperatures, the solution of Einstein equation admits one more scenario, which is kind of let me call it ADS5 black hole. So if you have a black hole, you have a horizon. But the black hole has also the UV brane here, sorry, the Planck brane here, which is not affected. But in front of that, there is a horizon, and all the other branes that I described you are behind the horizon, so you cannot see them. I said initially it's pulsar timing array collaborations. Yes. So, sorry, I said it initially. Maybe I missed. I didn't. But anyway, it's a collaboration of different experiments that they just gave the information of the stochastic gravitational wave background. So, okay, why that? Because now, as the temperature goes down, and of course as the horizon goes away, the branes start appearing. So the isometry group of this construction is the conformal group. So every time that you introduce a brane, essentially you break scale invariance. And of course, this model has a dual part from ADS-CFT, where someone can see maybe in a more straightforward way why we have a phase transition there. But the point is that every time that the brane appears, there is a phase transition. And since you break scale invariance, this is strong first order phase transition. And every time that you have a first order phase transition, you produce gravitational waves. So when the TV brane appears, you produce gravitational waves, a background in a specific frequency, not in the PTA. But however, when the next brane appears, the GV brane that I showed previously, the dark brane, then another set of stochastic gravitational wave background is produced, and this could be in the correct frequency, the correct order, according to where the brane is localized. So in that sense, this model also gives an explanation about the PTA, the stochastic gravitational wave background. So now, what is the message to take home based on this framework? The message is that, first of all, dark matter interacts, in our case, only gravitationally. And the tricky part of this is that by gravitationally, I mean that you perform some fluctuation of the metric. So you have tensor fluctuations, which is the graviton and the tower, the Kaluza-Klein stage of the graviton, plus some scalar perturbation of the metric, still within, essentially, the gravitational part, which is the radion, gives you the radion. So all the interaction that I'm going to show you here, and which gives me the correct relic abundance and all the other information, comes via the interaction with the radion. In that sense, is only gravitational interaction. There is no any other way that the dark matter candidate that I show you interacts with the standard model. On top of that, we have that, due to this, actually, we have that the dark matter relic abundance is obtained via annihilation into radians. So dark matter annihilates into radians and gives me the correct number of particles in the early universe. But when we talk about the direct detection and indirect detection accelerator searches, we have interactions with the standard model, so dark matter to standard model via radian. So you see, in that sense, we decouple these processes, solving the standard problem that WIMPs-like candidates have. And finally, as I said, assuming that PTA gives us some information about a new fundamental scale in physics, which is around GeV, we can say that if our dark brane is in that scale, we can also predict the existence of that signal. Plus, that if we assume that, we can very, very much constrain the range of the parameter range of the mass of the dark matter, also making the experiments to be more concentrated in some specific searches. So one more thing is that, of course, Randall-Sundrum model comes from 2000, and many things have been done on this. And there are some also other papers that having dark matter, but usually they use two branes, the one that I showed you previously, without solving almost any of the problems that I described. And also there is, recently there was another model with three branes, but essentially they have many differences with our case, not even putting the dark matter on the third brane. So in principle, what I want to say is that, according to my knowledge, this is the first, our work is the first effort, essentially, to use this extension of the Randall-Sundrum model with some dark matter candidate, which can give you all these nice features and solutions, so according to my knowledge. So now, in order to follow all the next discussion, which could be also a bit more fino, in some sense, I will show you this, the main ingredients that you need to know. So as I said, we have the low temperature Randall-Sundrum metric. We perform some fluctuations. So these fluctuations can give you the radian, a tower of radians essentially. We care only about the lightest one, so n equals 0. We keep that, and this is what we care about. And now, as usual, after you do that, you integrate out the extra dimension, you play the standard game, and you end up with some effective Lagrangian. So the effective Lagrangian of the radian, of course, radian is a scalar field, so you expect that it couples to the trace of the stress and its tensor in each brane, and this is true. So we get the effective Lagrangian interact of radian with the branes via this term, and this is the coupling. And based on this, we can also obtain an effective Lagrangian about the interaction between the standard model brane and the GeV brane. And this is given by this coupling. This is given by this coupling here, and everything is based on this discussion. So let me move forward to tell you that essentially this model has three parameters, which is the scale of the dark brane. It is the dark matter mass and the mass of the radian. All of these are the only freedom that we have. So what we have initially, after integrated out everything, we have essentially a soup of particles in high energies, if you like, which is the dark matter. The candidate, it's the dark matter candidate that we have is the standard model content and the radian. All of them, they are in thermal equilibrium, and they have a very non-trivial way to disentangle, decouple. So we have to solve, of course, numerically, the Boltzmann equation, which are here. And this is what we do for now on. And let me show you the relic density, how it is obtained. So we parameterize everything according to the standard picture about what we have observationally about the relic abundance, and according to some critical thermal average. So we have to search to see about our thermal average, how big or small is compared with that. Doing all this procedure, but starting with radial mediation between the dark matter and the standard model. I'm giving you here only the fermionic part because it's the highest, and then for gluons and photons is either similar situation or worse. We see that we calculate the cross-section, we calculate the thermal essentially cross-section at the end, and for some relatively reasonable numbers, like dark matter candidate to be smaller than 10 GeV, which is essentially the scale, could be the maximum scale of the GeV brane in order to have the stochastic gravitational wave background under control that I said previously. And for the TV scale to be around 1 TV or a bit bigger, but not much, so you solve hierarchy problem with not much fine-tuning. You see that our thermal cross-section is 5 orders of magnitude smaller than the expected one. So this So the interaction between dark matter and standard model does not give you the correct relic abundance. However, as I said previously, we have one more set of interactions that we have to take into account, which is the dark matter with the radion. Because the dark matter with the standard model, what it gives you, the previous discussion, is that it can give you a temperature where the dark matter is decoupled from the standard model thermal bath, but it's still coupled with the radion. So there is a sub-thermal bath in that sense. And we calculate again, similar way, the cross-section is much more non-trivial, but at the end, I show you here in these contour plots that indeed there is a set of parameters here for the scale of the dark brane and the range of the mass for the dark matter, that it can give you the correct relic abundance. Here is the correct relic abundance, this yellow, this red line here, and these numbers here corresponds to the ratio of the mass of the dark matter over the temperature that it freezes out, and this is around 24, so it is called dark matter, correct in that sense, according to observations candidate. And if now care about the PTA that I said previously, then I should zoom in here, and indeed again there is a specific line that gives me the correct dark matter relic abundance, and as you can see, it constrains already a lot the possibility to have a correct dark matter candidate. This is the mass range now. It's really constrained. So since I show you that I can get indeed in this simple framework a correct dark matter candidate, let me show you how it compiles under the constraints that we have observationally. So I will speak about the direct, indirect, and collider information. So starting with the direct detection, we need, essentially what we need is to see how dark matter interacts with the nuclei. And this makes us reparameterize our effective Lagrangian so that the dark matter interacts with the fermions, with the quarks, and this is the effective coupling. Of course, this is a very non-trivial calculation to be done for the form factors, but it is already done, so we can just use it, fortunately. And we calculate in that sense our cross-section, which is inverse proportional to the mass of the radion square, to the fourth, which means that this discussion here just gives us some extra constraints on the radion on the mass of the radion. So in that sense, putting all this information from these collaborations together, plus the PTA here, I can show you that in this very, very constrained range for the dark matter mass, there is a very small window, but still big enough for the radion mass to be, so this model to be alive, and to predict the correct relic abundance, and to have some, not to be excluded by the experiments, okay, and also to have the PTA information. And I can play the same game with the sub-GeV range for dark matter mass, and also it gives me a nice window here, but I will explain more later on. So next, I can go to the accelerator searches. For the accelerator searches, the first part, for the first part here, it just gives me again a bound on the radion mass. So it's just simple with the previous one, so it's not so important here. But if I go to the sub-GeV scenario, then I can have information from the fixed target experiments at CERN and SLAC, and now they can probe a new boson, essentially the radion, and this can happen if we talk about invisible decay, because we care about missing energy events in some detectors. So you have, in that sense, in order to have an invisible decay, and since our parameter space is such that the radion mass is smaller than the dark matter mass, it means that the radion can decay only to standard model particles. And in that sense, in the detector, in order to be invisible decay, means that we should wait, or the dark matter radion mass should be such that the radion is decay after is produced and decay outside the detector. So this gives us some bounds on the radion lifetime. Yes, you can do that because a free parameter, right. And the radion mass is a function. Okay, this is a good question, and it could be according to how small is its mass. What do you mean? Depends on the interaction. Yes, it could be, but there is a range where the dark matter mass, if it is smaller than a specific case, and I will show you about this, for the radial mass, then this could be indeed the candidate, but in this range that I'm talking about, this cannot be, because we checked that, okay. So in that sense, we check about that, putting all the information about the PTA, putting the information about the invisible observations, let me put it that way, that we want to do. We see that the radial mass, the scale of the dark brane is also constrained, and the radial mass is very constrained because we are only left on this small window here. So again, this is some bounds on the radian mass. And finally, the most important point for now, it comes from the indirect detections, but okay, this can be separated in two parts. One part is about having CMB information on cosmic rays and galactic information from galactic center, but these are bounds on the thermal cross-section for our candidate, and we pass them because it's much, much smaller than the constraint that they give, so this is not very important for us. However, the BBN itself, the Big Bang nucleosynthesis, can give us some real constraints, and the first point is that all this discussion that I showed you previously about and solving the Boltzmann equations and having all these nicely distributed particles and decoupling has to do with the requirement that the radion is in thermal equilibrium before, with standard model, before dark matter freezes out. And all this busy plot is narrowed down to this parameter here, essentially the ratio between the temperature that radion freezes out over a temperature, and for our case is the temperature that the radion freezes out over the temperature that the dark matter, the temperature that the radion freezes in over the temperature that the dark matter freezes out. And this should be much, much bigger than 1. It's a simple ratio. And according to this, we can put some bounds on the radion mass and the radion and dark matter physics, according to what I described previously. So this can be indeed achieved if the radion mass is above 2 times the electron mass, so above some few MeV. Then this sigma is bigger than 1. All this previous discussion works fine, as I explained, and then I can reparameterize the lifetime of the radion according to these values here. And as I said, if the scale of the standard model brane is around 1 TeV, the scale of the dark brane is around 1 GeV in order to have also the PTA. And then if MR is around few MeV, the requirement that the radion should decay before like smaller than 10 seconds is achieved, and this can be a really good candidate for a spin-off. So we have the dark matter candidate and a spin-off, which is the radion. However, there is another region where the radion mass is smaller than 2 times the electron mass, which is divided in 2 subregions. The first region, which is till 10 keV, is excluded. We checked that it is excluded. First of all, we have to recalculate all the Boltzmann equation and everything, because now the radion is out of equilibrium with the standard model when dark matter freezes out. And still, we see that the lifetime is much bigger than 10 seconds, so it's excluded by the BBN. And here I present you some contour plots, including all the previous information that I show you. So this is the open window that we have. Again, very constrained on the radion mass and very constrained on the dark matter mass in the GeV scale, and the same, okay, and I'm almost done. Also in the sub-GeV scale. And here is similar information with all the constraints added in the case that regarding the lifetime of the radion. And still, we see that there is a small but relatively interesting, I would say, window for observations here. But if you go to the as I explained, if you go to the sub-GeV scenario, then the lifetime starts becoming really, really bigger than the needed one, and this can be excluded. However, and I'm finishing, I'm almost done, there is the second subregion that I described, because the one subregion is a radion mass smaller than 2 times the electron mass, but bigger than 10 keV. This, as I said, is excluded. But however, and this is related with your question, is that there is a scenario where radion could be really, really, really light. This is included in the scenario of ALPS, like action-like particles, and in that sense, one may not need the dark matter candidate that I showed you previously, but this is something ongoing that we're doing now. But in any case, someone should be really careful. For example, this is just a naive estimation for now about the effective relativistic degrees of freedom that you introduce around the BBN time, because it can affect the whole history of the universe. So in that sense, what we find is that if there is kind of candidate like this, and first of all, it will create a relic background of radions, could be in principle observed like neutrino background that we have, but we have to be sure that this radion is decoupled from the standard model around the QCD scale. Otherwise, we will have a very big shift in the relativistic degrees of freedom that we don't see right now, and messes up a lot with the evolution of the universe. And with that, I would like to conclude and essentially tell you the message of this work is that with a simple extension, essentially, of the gravity part, and with a simple extension of the Randall-Sundrum model by one extra brane, you can include and you can predict many nice things. First of all, that you can have a dark matter candidate which interacts only gravitationally, in the sense that I explained with the standard model. And you can decouple the process that gives you the correct relic abundance from the process that gives you constraints from observational constraints. And then you, based on all of this information and based also on the PTA, you can have also a very narrowed window about the possible dark matter candidate, about the mass of the possible dark matter candidate. You can see that it is like around 150 MeV to a few GeV to GeV. So this can really sharp the experimental searches. And on top of that, you can have a spin-off in that sense, which is the prediction of a light radion, which can also be observed in some fixed target experiments like NA64 and LED Max, as I explained. And for some future plans, which are connected with the last slide that I showed you previously, we are essentially now working on the ultralight radion cosmology, when the radion is like less than 10 keV essentially, but around 10 to minus 15 or something EV, the mass. And we try also to incorporate in these models the correct way to describe inflationary scenarios, because as far as I know, after 2001, 2002, from the work of Peloso et al. And Grosjean et al., people have stopped discussing about this without any real concrete reason why, if I'm not wrong. So now we try to extend this information. And with that, I would like to thank you for your attention.
On page 13, you flash some system of differential equation.
13?
The Boltzmann.
Here.
Yeah, that's one.
Yeah.
You didn't seem to elaborate after this.
Yes.
But are they in static solutions? And if there are, then are they stable?
Yes. Yeah, the solutions are stable, especially if you do it. Okay, there is, as I said a bit, there is the requirement for, especially our case, that the radion is in thermal equilibrium, and this shapes essentially the form of these equations. When you have this assumption under control, then all these solutions are stable solutions.
So if you put the derivatives to zero, can you solve them?
Well, yes. You actually to put this derivative to zero, essentially it means that your number density is constant. What does it mean? Yes. But okay, this means that essentially you are in thermal equilibrium. So when you putting that to zero, it means also that the right-hand side altogether goes to zero, and essentially it gives you a constant solution. Maybe it's more easy to see in. Because here it's okay. These are the different interactions, so you can forget about this.
The result is zero anyway.
Yes, it's because it's a constant solution.
Yeah, I have a basic question about the setup. So you have three brains.
Yes.
And you put them in specific places. Is this an assumption, or is this something that comes from dynamics?
Well, okay, this is a good question. So, okay, if I had only the two brains in the standard case, the assumption is that I want to solve hierarchy problem, and then I have to put the Goldberger-Weiss field to stabilize it in this specific direction. In this scenario now, it goes like opposite in the reverse way, because I assume, okay, that I want to also to explain PTA. If I want to assume to explain PTA, then the dark brain has a very narrow range of scale that it can be put. So the PTA tells me where is this brain, and after I put that brain, everything follows in order to solve also hierarchy problem, and in order not to have anything on the UV brain.
So is it a five-dimensional system of equations with this system solved?
Yes, exactly. Yes, but it can be divided into two parts. UV to standard model brane, and then standard model to dark brane. So you have two sets of all these equations, of Einstein equations, essentially, in the 5D picture. So you have two constraints.
But calling this a solution of the hierarchy problem is a little bit
You're
naive. Let's put it like this.
you're,
That's what people thought at the time. But now we know that you just fine-tuned your problem.
you're right. You're right. Actually, it's a good. Both are good points, and I agree with you. I totally agree with you. The point is that, which also is related to the last thing that I said, which is the following. So now PTA gives you information about the dark brane. If you want to solve, if you want to explain the PTA, you have the dark brane. The question is what you said exactly. Why I should fine-tune now the TV brane in that specific scale? And we think that the question can be answered in maybe more concrete way if you try to have the correct inflationary scenario in this model, because maybe you add extra branes, or maybe you add some other physical scale, and maybe this can ameliorate a bit the fine-tuning of the TV brane. I follow you, but let me try. But thank you for the question.
Okay, we are late already. I cannot ask.
So I have a PTA is about photons, right? If I remember
No.
well.
PTA is about the gravitational wave, stochastic gravitational wave background. Yeah, sorry for not being so explicit on that, but it was too fino, and I'm not too fino to keep.
So this is, let me say, this gives you bounds on the dark matter mass scale.
Yes, implicitly, because this. So as I said here, maybe let me put it more concrete. Okay. So as I saw here, this is the high temperature solution of the Randall-Sutter model. So there is a horizon, right? So every time that a brane appears, gets out of the horizon, you break scale invariance, and every time that you break scale invariance, you produce some gravitational waves. So in that sense, PTA, if you want to explain this PTA, your dark brane should appear around GeV scale. That's the point. Okay, thank you.
Okay, thanks again.
Thank you very much.
So, the last speaker of this session is Evangelos Avtsonidis. Talk about boundary entropy function for interface conformal field theories.
Thank you very much, and thank you for the invitation to present my work that appeared like a week ago in collaboration with Andreas Karts from University of Texas at Austin. So I'm going to shift gears and I'm going to talk a little bit about holography and entanglement entropy, and in particular I'm going to be focusing in this boundary entropy function for interface conformal field theories. All right, so the contents of my talk, well, I'm going to be quick so we can enjoy lunch also because we're running out of time. So I'm going to review a little bit about interface conformal field theories. Then I'm going to talk about the holographic setup that we used. And then I'm going to spoiler alert, I'm going to talk about the non-universality of this boundary effective function. And last but not least, I'm going to talk a little bit about constraints on this boundary entropy function and a holographic proof of it, of this G effective. So let me first start with a review of interface conformal field theories. So ICFTs, or interface conformal field theories, can be seen as a more generic case of the boundary conformal field theories. Namely, in a usual case, you have, in a general case, you have two kinds of conformal field theories, a CFT on the left and a CFT on the right, with central charges C left and C right. Then, when you compute the entanglement entropy, you have this entangled region A, and then okay, you can have the interval L left that lays on the left side of the interface, and the interval L right that lies on the right hand side of the interface. And the interface is denoted here by black. So you can reduce this ICFT system into the BCFT system by just folding x to minus x. So you just you just map all the x's to minus x's, and then you reduce the system to a BCFT. And then the boundary, the entanglement entropy is given by C left plus C R, so the sum of the two central charges divided by 6, times the log L over epsilon. Epsilon is a UV cutoff, L is the sum of L left plus L right, and then you have this log G. This log G is the boundary entropy number, right? This was shown by Calabresa and Cardi. All right, but when you have a more generic, let's say, setup, so when you have two different CFTs that might have also the same central charge as we are also having later on, then the boundary entropy number is getting promoted to an effective boundary entropy function that depends on the ratio L left over L right, as noted by here. All right, and a few things are known about these quantities. So we just try to understand if it's universal or other kind of constraints that one can impose for this G effective. All right, so let me first try to describe the holographic setup that we're having. And first, let me start by describing what holography is. So holography suggests that we have a low-dimensional non-gravitational theory that could be gauge theory, that could be matrix theory, that is dual to quantum gravity theory. And it was made explicit by Maldacena in the ADS-CFT correspondence that on the gauge theory side you have an n equals to 4 super Young-Mills in 4 dimensions with SUN gauge group, and on the gravity side you have a type 2B string theory on an ADS 5 crosses 5. So the gauge theory lives on the boundary while the string theory lives on an ADS bulk. All right. There is also a holographic prescription on how to calculate the entanglement entropy using holography, and this was done by Ryo and Takayanagi for static and asymptotic ADS spacetimes. This is pretty easy to understand. So you have the boundary, which is a CFT in D dimensions, and you have the bulk in an ADS D plus 1 dimensions, and then the entanglement region is A. You want to trace out the beam. So if you want to compute the entanglement entropy holographically, what you do is you consider this gamma A, which is a surface that should be homologous and have the same boundary as the entanglement region A, and then you can just minimize the area of this surface divided by 4G, where G is a Newton constant, right? So we are going to focus in 1 plus 1 CFTs, so in 2 plus 1 bulk theories, and then this gamma A is just reduced to a geodesic. So it's just a computation of the geodesic. And these gamma A's are called the minimal area surfaces. All right, so the holographic setup in our case is given in this sketch where you have, well, it's not shown, but this is the interface there. Then you have on the right and on the left side, asymptotically ADS spacetimes, you have R, which is a coordinate, that runs from minus infinity to plus infinity, and X, which is a radial coordinate. So a conformal defect spacetime in 2 plus 1 dimensions is given by a metric given like this, where e to the power of 2AR is the warp factor. And then you can see easily that if you choose that the warp factor is cos R, you reduce the metric to a pure ADS3 case. So we use metrics of these forms, of conformal defect spacetimes. Then it's really a trivial procedure that you wanna compute the geodesics. So you just plug in this metric into the, you compute the geodesic, and you can see that the minimal RT surfaces, the Ryo-Takayanagi surfaces, are given by Lagrangians of this form, right? So I didn't mention, but these kind of metrics are describe ADS2 slices of an ADS3. So these blue lines are ADS2 slices in an ADS3 spacetime. And in these ADS2 slices, you are having a scale symmetry. And this scale symmetry have a nether charge, which is denoted here by CS. So this CS is a nether charge for the scales. And you can see that the scale symmetry gives you a differential equation of this form, right? So we want to have essentially a parameter, which is the nether charge CS, that can somehow manipulate and give you information about this ratio that you want to have in the boundary entropy function. In principle, you can see that if you choose CS equal to 0, then you reduce the system into a BCFT, where you have the L left and the L right to be equal and given by L over 2, where the sum of those give you L. The interesting case is when CS lies in between 0 and the minimal warp factor, EA star, where it gives you non-trivial ICFTs, where in principle you can choose plus or minus here, and this plus or minus here is getting depicted by having L right bigger or equal than L left. And also you can have CS to be equal to the minimal warp factor, where in this case it gives you an L left equal to 0. You can also have CS's larger than the minimal warp factor, but these are RT surfaces that lie on the right or on the left part on the interface. So we're so here or here. So we do not really care. We care about RT surfaces that can take information about the interface, right? Okay, so one crucial thing is that the relation between CS and the ratio is highly non-trivial. And actually, what I could found is an analytic form of this relation only in the Super-Janus solution that I'm going to describe later on. So the setup is given like that, and then you can pick your favorite warp factor. That could be Janus, that could be Super-Janus, that would be Randall-Sundrum models, and then you can do the computation. So let me hop on to non-universality of J effective. So we studied Super-Janus in much detail, and Super-Janus comes as a type 2B solution that is asymptotically ADS3 cross S3 cross M4, and this M4 can be either the 4 torus or a K3 manifold, where we have choose the 4 torus, and then what you can do is you can compactify into 3 dimensions, because we care about 2 plus 1 bulk. So what you can do is you compactify the torus, and then you compactify the S2, and then you compactify the compact part of the fibration on the Super-Janus metric. Well, the end point is that you have a metric given as such, where theta is the action and psi is the dilaton that jumps into when crossing the interface, right? Okay, and R is the ADS3 radius. So CS, as I told you before, takes values between 0 and the minimal warp factor, where you can see that the minimal warp factor in this case is given by 1 over cos psi times cos theta. And then it's a trivial procedure to just solve for the XR on the previous differential equation that I showed you, regularize the integration limits, which is an important thing to do when you compute the geodesic, and then the boundary entropy function is given in this plot. Well, first of all, this kind of computation cannot be done analytically, so we just employ numerical methods. Here you have log G effective, so the boundary entropy function in terms of the ratio, which is not really shown here, L left over L right. And 2 crucial things that you can see. First of all, these different curves serve for different choices on the radius, ADS3 radius, and also of the action and the dilaton, where here we have taken theta to be equal to 0 anyway. So 2 cases that are important. One is that the curves blow up near the maximally asymmetric interval. So this is something that we expect, of course, and this is something that we actually see. And also another thing is that these curves attain the boundary entropy G number when the ratio approaches to 1, which is something that suggests that the computation is actually right. One more thing. Well, I'm gonna mention it later anyway. Okay.
So what is the vertical axis?
This is the boundary entropy function, the G effective, log G effective. This boundary entropy function, let me remind you, is this additional piece that serves as perfect. Okay, so this, yeah. Here you calculate the minimal area, and then you subtract the ADS3, the pure ADS part, yeah. All right, but we wanted to see if this G effective is universal or not, and I have already spoiled you that it's non-universal, right? And in order to see this, we took 2 solutions, the Janus and the Super-Janus, and we wanted to have both solutions the same G number, so they start from the same G number here when the ratio is equal to 1, and we wanted to see if both of the plots have the same profile or not. And of course, you can see that these profiles are different, which suggests that G effective is non-universal. Well, log G effective is non-universal, and it depends on the details of the underlying theory, which suggests that the G effective knows about the full warp factor, knows about the geometry, knows about the theory that you are having, and cannot really be fixed by conformal symmetry. So this is something new and something interesting, because people didn't really studied, let's say, asymmetric intervals around the interface before, and this shows that the G effective is non-universal. All right, but we also saw some things about the constraints that one could impose on the G effective. Namely, we wanted to see if we can get any kind of constraints from strong subadditivity. Well, the strong subadditivity inequality is given as that, where A and B are the two regions, and you subtract, let's say, the union and the intersection, and this needs to be greater or equal than 0. Then we wanted to prove the entropic G-effective theorem from SSA, the strong subadditivity. So we consider two light-like, well, first let me explain this. You have the interface, this is 1 plus 1, right? You have a time-like interface, you have X on the two axes, and here you can see that the right, the LR is bigger than the L left, and you take two causal light-like regions, starting from sigma comma sigma and starting from minus S comma S, and then you want to impose, let's say, the stringent SSA condition on such a setup. Namely, what you can do, you consider the light-like limits when U goes to S, when U goes to S, and when phi goes to sigma. Then it's crucial to see that SA, so this part, picks up a contribution from the interface. So SA is given as a sum of two terms, S int this one and this one, right? And S int is given by this, or C over 3 log L over epsilon plus log G effective. And also the union picks up a contribution from the interface. All right, and then the other two regions, the intersection and the B, do not have any kind of contribution, and they are given by this peculiar, let's say, well, form, where all these are parameters that we can choose however we like. All right, having taken this, we can take, in addition to that, the limit when V goes to W and he goes to kappa, and then the SSA takes this kind of form where eta and delta are infinitesimal and positive constants. Finally, the final step is we assume the W and kappa to be negative and sigma is S and sigma to be very small, and then the SSA gives you the tightest bound of this form. And then there are two kinds of conditions that you can impose. First, you can remain in the ICFT, and you can think that log G effective is only dependent from the ratio. If that's the case, then you get this G effective theorem that suggests that D log G effective over D rho, where rho is the ratio, is less than or equal to 0. Another thing that you can also do is you can trigger RG flow. Namely, you can assume that log G effective is both a function of the interval and the ratio. And in that case, I haven't written it down, but you get another G theorem that boils down to the BC effective G theorem of Takayanagi, but is given as from a more, let's say, weird and involved formula. Namely, in that case, when you trigger the RG flow, you get a D log over DL less than or equal from a D log over D rho. And this, I cannot really know what to think about it. Perfect, okay. So this kind of G theorem can also be seen by the numerical computation I showed you before. So we can confirm the monotonicity of this condition in 3 different examples. First, you have the Janus, the Randall syndrome brane worlds, and the super Janus solutions, where here you take different ADS radii for different curves. Here you get different turnaround points for the RS, and here you get different gamma for the Janus solutions. So they are also proven, let's say, well, not proven, but you see that this indeed holds in these 3 examples, so it should hold. Another proof that you can do is through holography. So you can actually write down a compact form for G effective in terms of CS. And that would be given your favorite warp factor, EA. You can put it in here, and then you can just compute log G effective immediately. Here what we see is that we have subtracted the divergent pieces, minus log 2L, minus log 2R. And so in order to show that d log g effective over dr is less than or equal to 0, you can actually take a derivative of d log g effective with respect to dcs. You can see that this is positive. All right? Then from the scale symmetry, you can solve this, and you know that x when r goes to infinity and x where r goes to minus infinity gives you LR and L left, respectively. So you get a form for the ratio of this form, and then you can just take a derivative of this with respect to CS, and you can see that this is negative. So just employ the chain rule, and then you can see that d log g effective with respect to the ratio is negative, less than or equal to 1. So there are concrete examples, as I've showed here. There is holographic proof, so I think it should be right. So I will conclude, because we are also running out of time, with things I find interesting in this ICFT business. First of all, I would like to see if one can have a C theorem for this effective central charge, where the effective central charge appears when you take L left or L right equal to 0, and then you get this additional central charge in the coefficient of the log piece of the entanglement entropy. It's also connected with transmission coefficients and things like that. I would also like to understand if there is a replica trick, a method by Cardi Calabrese for the asymmetric interfaces around intervals around the interface. And also there are the questions about higher dimensions, if you can impose, I don't know, some kind of F theorem or A theorem for higher dimensional cases, because here we are in a 1+1 CFT. So I guess with that, I would like to thank you.
There is a way of doing this unambiguously by adding a counter term. But so I'm not sure if the ambiguity you're referring to is related to this or not.
What ambiguity you're talking about that I was referring to?
Epsilon to 2 epsilon.
Yeah.
This changes to 3.
No, I mean, you said in the end it's not universal, right?
Yeah, right.
So is this conclusion related to the statement that you can rescale epsilon or?
I'm not sure about that. Yeah, I mean, if you change epsilon, you essentially change the G number, right? I would say that it's more of, okay. In this case that you are talking about, this log G is just a number, right? But when you are considering L left and L right that are not equal, then this G becomes a function of LR over L right. So how would you, I mean, there is an extra ambiguity because this G depends on the ratio, right? And this extra ambiguity, I think it's being shown here, because I mean, you can actually see that the log G effective depends on the ratio, and it's actually, non-universal here.
I think there is one way to define this unambiguously, because otherwise what is said is correct. And this is to define the difference between G with the interface and without the interface, in which case the divergence is.
Well, it was essentially the same question, and yes, that was also my understanding, that one needs to define some relative entropy, entropy of this system with respect to the entropy of the other system and so on, or at least pick a particular regulator at epsilon away from your brain or whatnot that everyone agrees on.
Yeah.
Either or.
Yeah. Yeah.
In the computation you performed, you solved some classical equations of probe type of actions. Experience in the past shows that depending on the parameters that you have, these solutions might not be stable everywhere. I don't know if you have examined this.
You're talking about this, right? About these examples?
Some equations, yeah, I guess so.
Yeah.
It's for the Rita-Chiaraganaki surfaces, right?
So you have,
Yeah, okay.
So I'm referring to computation like QQ bar type of potential that we performed even starting in the early days of ADS-CFT. And now if you have problems, models with enough parameters, then the fact that you have some classical solution doesn't mean that you can trace it as far as stability.
Mhm.
So you have to look at the fluctuations if you
Mhm.
have negative
Yeah, no, we haven't.
modes,
We haven't studied any kind of fluctuations or something like that. Yeah, you're right.
Yes.
In general, when you have a setup with an interface, the quantities you are computing don't depend only on LR over left, but also what kind of couplings
Mhm.
you have on the two sides.
Mhm.
This somehow doesn't appear in your computation. Are you assuming something about this?
Here we're just assuming that in both sides of the interface the central charge is the same. That's what we are just assuming. We are not.
So you mean
I have.
is the space ADS in between or not?
Well, it's asymptotically ADS here, right, on the
It's
boundary.
only asymptotically ADS.
Yeah, yeah,
So
yeah.
in general, then you have running fields, right?
Yeah,
So these have sources at the boundary.
that is true.
Therefore, what you're computing, G2 effective, G effective, depends also on these sources.
Yeah.
But you don't vary them, but
No.
you only left, and I'm not sure how you do it without varying the other.
Yeah, maybe what you're saying is that we're doing things naively, right? That's what you're.
I don't know if it's
Yeah.
or not, but some species of the discrete
Yeah.
Use the geometry, right? You don't use the geometry.
Yeah, we just use the geometry indeed. Yeah.